Hello, and welcome to the full course session on FEA using SOLIDWORKS, a powerful tool for conducting advanced finite element analysis. This is a certified course session, so after completing the session, make sure to fill out the form in the description to claim your certificate. You can proudly share your achievement on LinkedIn to showcase your new skills. At Skill-Lync, we're dedicated to providing industry-relevant advanced engineering courses. We partner with industry experts to offer top-notch training that equips you with the skills needed to excel in your engineering career. Don't forget to subscribe to our channel for more insightful tutorials and updates on engineering tools and techniques. Hit the subscribe button and stay tuned. Here's a brief overview of what we'll cover in this training video. In the first chapter, we'll start by understanding the basics of FEA. We'll cover what FEA is and the different types of analysis methods, including analytical, experimental, and numerical methods. You'll learn how to perform FEA using a cantilever beam example and review stress-strain plots. We will then discuss the general steps followed in FEA and dive into mesh elements, focusing on H refinement and P refinement. We'll summarize the key points to wrap up this section as well. In the second chapter, we'll explore the different types of FEA analysis available in SOLIDWORKS. This includes structural analysis, static analysis, and dynamic analysis. We'll explain the differences between static and dynamic analysis and also cover linear and nonlinear analysis. In the third chapter, we'll get familiar with the SOLIDWORKS simulation environment. We'll begin with a recap of important SOLIDWORKS modeling features, then introduce SOLIDWORKS simulation. You'll learn how to perform a simple cantilever load analysis, including a review of SOLIDWORKS sketch and features, as well as how to navigate the simulation interface effectively. In the fourth chapter, we'll cover how to perform basic FEA analysis using SOLIDWORKS simulation. This includes static linear analysis, static nonlinear analysis, and dynamic linear and nonlinear analysis. We'll guide you through the processes and methods for each type of analysis. In the fifth chapter, we'll discuss how to simplify complex 3D simulations into simpler 1D or 2D simulations. We'll explain when to use 1D, 2D, and 3D simulations, as well as demonstrate how to perform each type in SOLIDWORKS. In the sixth chapter, we'll explore the design study feature in SOLIDWORKS. You'll learn about parametric studies, including their advantage and how to access and perform a parametric study. We'll use a wine bottle example to illustrate optimization and evaluation of design scenarios. In the seventh chapter, we'll delve into buckling analysis, an important simulation in structural engineering. We'll discuss what buckling is and how it differs from bending, and the relationship between buckling shapes and fixture types. We'll also show you how to perform a buckling analysis in SOLIDWORKS. In the eighth chapter, we'll cover fatigue analysis, which helps determine if a model is prone to fatigue damage under varying loads. We'll discuss the application of SN curves in fatigue analysis and perform a stress analysis of an S hook. We'll also cover various fatigue studies, including constant amplitude, variable amplitude, harmonic, and random vibration analyses. In the ninth chapter, we'll review drop tests, which are used to assess how well an object withstands impacts from various heights. We'll cover how to access drop test features in SOLIDWORKS and perform a drop test on a PCB board, discussing the results. In the 10th chapter, we'll examine frequency analysis to determine the vibration characteristics of a structure. We'll discuss the reasons for performing frequency analysis, natural frequency, and resonance, mode shapes, and types of solvers in SOLIDWORKS frequency analysis. We'll use performance frequency analysis on support brackets and discuss the results. Thank you for joining us. We're excited to have you on this learning journey. Make sure to subscribe for more updates and detailed tutorials. Complete the training, earn your certificate, and share your achievements on LinkedIn. Let's get started with FEA using SOLIDWORKS.
I hope you're doing well. So welcome to the very first session of finite element analysis using SOLIDWORKS. In this course, we will be learning how to perform various types of FEA analysis according to the problem which is given to us. And we will be doing all this analysis work using the SOLIDWORKS simulation software. So the table of contents for the week were, first we'll learn what FEA is, and then we will look at the different types of analysis methods. The first one is the analytical method, the second one is the experimental method, the third one is the numerical method. And after that, I'll give you a brief explanation of FEA with the help of a cantilever beam. And then we'll talk about the stress and strain plot. And after that, I'll give you the general steps which are followed in solving any FEA. And we'll just talk about the mesh elements, the H refinement, the P refinement. In the end, I'll talk about the different types of analysis which is covered in the course. and just we'll have a summary. So before we jump into the software part, let us first understand what finite element analysis is and why do we use it. In simple terms, finite element analysis, which is abbreviated as FEA, is just one of the many methods which is used to solve engineering problems. To show you how FEA differs from other methods, let us first look at the more traditional methods of solving problems that you guys might be already aware of. So there are three main methods for solving engineering problems. The first one is the analytical method, the second one is the experimental method, and the third one is the numerical method. So let's talk about each of them now. So the first one is the analytical method. One of the ways of dealing with engineering problems is the analytical approach, and you would probably be more familiar with it since this is the approach followed for most of the problems you solve in school or college. An analytical approach is when you are given a problem with all the inputs or initial conditions, and then you use a set of mathematical formula which you either derive yourself or you directly use the formula some researcher has already derived, and then you just solve those mathematical equations to get the final answer, which would also be the solution to your engineering problem. A very basic example of analytically solving something would be, let's say I just drop a ball from the top of a 100-meter building and I ask you how much time it would take for the ball to reach the ground. So in this case, your initial conditions would be the initial velocity, which is 0, the height of the building, which is 100 meters, and the acceleration due to gravity, which is 9.8 meters per second. And to solve this, you don't need to derive any equation since Isaac Newton has already done the job for us. You would directly use the Newton's equation of motion, input the values, and get the final answer, which could be the time it takes for the ball to drop. So this is called an analytical way of solving the problem. As long as the formula you are using correctly represents the situation, the final answer which you get would be very accurate, but there are some problems that might occur in this approach which we will look into in a short while. Another way of arriving at the solution to any problem would be the experimental approach. So here, as the name suggests, you will carry out actual experiments and record the results to get the solution. So if we take the previous example of a ball dropped from a building, then someone would have to throw a ball from a height of 100 meters and someone would have to record the time it takes for the ball to reach the ground using a stopwatch. So here, as long as the experimental setup is correct and there is no issue with the recording device, the solution would be accurate. But even in this method, there are some issues which might arise, which we will take a look in a short while again. And one more method that can be used to solve engineering problems is the numerical method. The numerical methods are mathematical tools used to acquire approximate solutions to the problems. Now, some of you might wonder how we can get solutions to a problem using approximation. So to explain this, let's take a very simple problem. Here we have a circle, and let's say I want to know the circumference of the circle, but I don't know any formula related to finding the circumference of the circle. So here I can place straight sticks along the circumference of the circle, and then I can measure the length of just one stick and multiply that length with the number of sticks which I have to get an approximate circumference of the circle. It is true that you won't have an 100% accurate result in this case, but you can get a much more accurate result by reducing the size of the sticks and also increasing the number of sticks. Another example would be, let's say you want the area under this curve, but you don't know anything about integration. So one way to deal with this would be to divide the area under the curve into multiple rectangles, and then you can calculate the area under the rectangle to get an approximate area which is under the curve. Similar to the previous problem, more the number of rectangles, the more accurate would be the result you get compared to the true value of the area which is under the curve. So there are probably 2 points which you might have noticed. One is that even if you don't have a proper formula for solving something, you can still get an approximate solution using numerical methods. And the second is that the solution you get from numerical methods is not the exact true solution, but still it is very close to the true solution. So all of these three methods have some advantages and disadvantages, and the use of one of the methods would be preferred over the others based on the situation. So to get a better understanding of how these methods translate to engineering problems, let us also take up another very simple engineering problem that you guys probably would have come across. So this is an image of a cantilever beam. A cantilever beam is basically a beam which has one side fixed and the other side is free. So here I would like to check what would happen to the beam if I apply some force at the free end of the beam. And when I say I want to check what would happen, I specifically want to know how much the beam would displace from the default position after the load is applied. So first, let's see how we can analytically solve this problem. Again, luckily for us, we have a differential equation which describes how the cantilever beam will behave when acted by a force, since someone has already derived the flexure formula. But it's important to note that there are some basic assumptions made while deriving this equation. So it only holds true as long as our case falls within those assumptions. So here I is the moment of inertia, E is the Young's modulus, and M is the bending moment of the beam. And if you want to find the displacement of the beam using this formula, then you will have to get the value of the variable y in the equation. So since we have the variable y in the second derivative form in the equation, we will have to integrate the equation 2 times to get the value of y. After the first integration, you will get something similar to this equation. You can get the value of constant by putting some boundary conditions. In this case, dy by dx represents the slope of the beam. And since at the fixed end there is no deflection, we could input dy by dx as 0 at the fixed end of the beam to get the value of c1. And then we will be integrating it again to get the equation in terms of y. Again, the displacement at the fixed end would be 0, and you can use that fact to get the value of the second constant. And finally, you will have an equation for the displacement of the beam. Substitute the values for known constants and you will get the final answer. So this was the analytical way of getting the displacement. If you want the same answer using experimental approach, then you would have to set up this model with proper dimensions, apply the correct force, and then you can manually check the displacement of the beam. Now let's look at how we would solve this problem using a finite element analysis. To solve this using FEA, we will have to split the entire beam into a number of smaller elements. For the sake of explanation, let's assume we split the beam into just 2 parts. In actual analysis, this beam can be split up to thousands of smaller parts. Here, each division is called an element, and the point between each division is called a node. Now, to check the displacement of each of the beam, a simple equation called F equal to Kx is used, where F denotes the forces applied on the beam, X is the displacement we want to find, and K is the stiffness of the beam, which is basically a measure of how resistant the beam is to deflection under forces. To get these values, matrix calculations are used, as the software cannot solve differential equations. First, the value of stiffness K are found for each of the elements using a formula similar to what's shown on the screen. Using these individual stiffness matrix for the entire beam is formed, which is known as the global stiffness matrix. And then by using basic relation previously shown, the displacements for the beam is calculated. In the displacement matrix, you can see 2 types of variables used, V and theta. The variables V1, V2 and V3 are supposed to give the linear displacement in the y direction for the nodes 1, 2 and 3 respectively, and the variable theta gives the angular displacement of the beam. So now that you know how to approach this problem by various methods, if I ask you to solve a similar problem, I'm sure most of you would prefer to go with the analytical approach, as it seems pretty straightforward with less calculations. And I agree that by just looking at this specific example, FEA might seem like an unnecessarily complicated approach to the problem. But a point to note here is that all the calculations involved in FEA are not manually done by us. All the calculations are done by the software. We just provide the model and the initial conditions for the software to run the calculations. And the second one is that the analytical approach seems significantly easier here, only because we already had an equation describing our setup and we didn't have to derive anything. Still, I would agree that using FEA for this problem is a bit of an overkill and we don't really need to use it. But then again, this is hardly a problem that an actual engineer would face while working in the industry. So why don't we look at how these methods hold up for real engineering problems? Let's say you are given a situation where a specific car model hits a wall at the speed of 120 kilometers per hour. And your task is to find out upon a crash how much of the passenger's compartment is damaged. The main goal is to minimize the damage as much as possible to ensure passenger safety. Now think about how you would solve this problem using the analytical approach. Heads up, there are no direct formulas which give the intrusion value for all car models ramming a wall at 120 kilometers per hour. I'm sure you can start noticing the problem with the analytical approach here. It is easy to deal with simple problems using an analytical approach, but as the complexity of the model increases, coming up with analytical solutions to a problem becomes significantly more difficult. Not to mention, while doing this crash test, there are multiple prototypes where the design and position of various parts will be altered. So you would have to come up with multiple analytical solutions. Even the experimental approach is unreasonable. Since you can't expect a new car to be made for every small design change and then crash all of those cars, the crash tests which you see are usually the final models of the car, which have already gone through many design alterations. So this is where FEA comes in. These types of analysis can be easily performed using many FEA softwares. You just need a 3D model of the car. You need to input all initial conditions and just let the software run the analysis. If there are any modifications in the design, you just need to add that change in the existing model. If there is any change in the test conditions, you just need to change the input conditions accordingly and the software will get the job done. So not only can you save a lot of time doing FEA analysis, you would also be saving a lot of money that would go into creating multiple prototypes. But here it's important to realize that FEA is still an approximate solution and may vary a lot depending on how accurately the test has been carried out. So even for a car crash analysis, once a final model has been decided, after running multiple simulations, an experimental setup is done with the final model to verify the results of the simulation. So now let's take a look at the topic of stress-strain plot. This graph which you see on your screen is a stress-strain graph for steel. On y-axis you have the stress values and on the x-axis you have the corresponding strain values. And these graphs are material specific, which means that for another material such as gold or copper, you will have different values. Now these graphs are all plotted through experimental results. So the way this works is, if you want a stress-strain graph for steel, then a steel rod will be selected and it will be subjected to tension loads to increase the stress of the steel rod. And they will keep increasing the stress value till the material breaks, and during the process a device will be used to keep track of the strain values in the rod. Then using all the stress and strain values, the graph is plotted. Now you might wonder, why do we need these plots? These plots help us in knowing how the material will behave when we apply load on any structure. Using these graphs, we can know if the load applied on any structure is safe or not. Also, when you perform any type of analysis in the software needs to be provided information regarding how the material will behave when a load is applied. If we apply a load of 100 Newton on a steel beam, or if we apply 1000 Newton, then the simulation results will obviously be different. But the software is able to create a proper simulation for the material because the information of stress-strain plots are already added to the software. So a user would just select the material for the model and the software will predict accurate behavior based on these experimental results. Now there are a few important points in the stress-strain plots which we will be discussing about. Initially, when the material is subjected to stress, the deformation or the strain which the material experiences is directly proportional to the stress values. This is represented on the plot by a straight line between points O and point A. Mathematically, stress would be equal to some constant multiplied by strain in this region. This mathematical equation is called as the Hooke's law. And the point A, which you see at the end of the line, will be called the proportional limit of the material, since stress and strain are found to be proportional to each other between points O and A. Another thing to note is that as long as the strain in the material is between these points O and A, the deformations in the material are elastic in nature. This means that if the material has a strain value below point A, then if you remove the load on the material will go back to its original shape. Similar to how a rubber band goes back to its original shape once you stop stretching it. Once the stress values exceed point A, the material will no longer obey Hooke's law, which means that the strain in the material will no longer be proportional to the stress value, and you can see that represented by a curve. But even between the regions between point A and B, the deformation is still elastic in nature, and if the load is released, the material will go back to its original position. But point B on the graph is the region after which the plastic deformation starts. So if you apply a stress value higher to the value corresponding to point B, then even after removing the stress, there will be some permanent plastic deformation in the material. This point B after which the plastic deformation begins is known as the elastic limit or the yield point of the material. After point B, you will notice that the graph has flattened. So in these plastic regions, even for very small increases in the stress value, the material deformation is very high. And this continues up to point C. So the point C at which the material starts breaking is the highest stress value that the material can withstand and is hence known as the ultimate tensile strength of the material. And if any metal is subjected to a very high stress, it doesn't immediately snap into two pieces. There is a gradual decrease in the cross-sectional area as shown in the image before the material completely snaps into two pieces. So this decrease in cross-sectional area will begin at point C, which is the ultimate tensile strength. Then the material will completely snap into two pieces at point D, which is called the fracture or the breaking point of the material. Here we will discuss the three main steps which are part of any analysis done using the FEA method. And to better understand what exactly happens in each step, we will be using the CAR model which we were discussing earlier. So the first step in any FEA analysis is called as pre-processing. Since FEA is used for analysis of a product, before we can get into using FEA, we need a CAD model of the product we are analyzing. So before we start pre-processing, we will be given a CAD model which we will be importing into a pre-processing software. After importing the model, we usually perform a quick check to verify that there is no issues with the model. Sometimes when you import a model into a different software, some issues like gaps in the model and self-intersections occur. But most of these issues can be easily fixed using automatic tools in the software. Once it is verified that there are no issues with the model is discretized into a number of smaller elements, similar to what we had seen in the cantilever beam example. And depending on the type of analysis, there are various quality parameters which the individual element must fulfill. So some quality checks are also performed after discretization to ensure that the mesh is good enough for the analysis. But since this is an introductory course into FEA, we won't be going into details of mesh quality parameters in this course. And in the end, we have to define the conditions of simulation that we want to run. This includes all the details regarding which parts of the model is fixed, where the loads are applied in the model, the values of the load applied, initial conditions of the model, the material of the model, etc. There are many softwares available for pre-processing such as Hypermesh, Answer, Nastran, LSDyna, and many more. The next procedure is processing. The processing involves the actual running of the simulation in the software. There's not much to be done from the user side in this step. The software does all the mathematical calculations required for FEA in the backend, and the output will be the simulation of the test being performed. Software such as Autodesk Simulation, Answers are usually used for processing. And in the end, we have post-processing. Post-processing basically involves the visualization of the data obtained from the simulation. And based on what the objective of the study was, you would either verify your hypothesis or select the best design. or you could recommend some changes in the design based on the results which you got. So we had previously discussed that models which work on using FEA are discretized to a number of small elements. This process of discretization is known as meshing. There are two types of element shapes that are generally used: the triangular element and the quadrilateral element. In basic triangular element, we would have 3 nodes, as you can see in the image, and in the quadrilateral element, we would have 4 nodes. The type of mesh selected depends on the accuracy of the result required and the computational time allotted, and thus may vary according to the application for which the meshing is done. In structural problems, we usually go for quad elements. For crash and non-linear analysis, we try to go for the quad elements, but some triangular elements may be necessary to capture the model properly. And for casting simulation, triangular elements are preferred over quads. Any model that we will be using for FEA analysis will consist of intricate shapes and profiles that cannot always be properly captured even after discretizing them. So the more complex the model is, the more is the number of elements used in order to get an accurate result. The process of discretizing the model more by reducing the size of elements and increasing the number is known as refining the mesh. So in order to check whether discretization, which we have done, is sufficient or not, we perform something called the grid dependency test. In grid dependent tests, we basically run the same simulation multiple times by refining the mesh up to a point where the result does not change even after refining the mesh further. In order to refine the mesh, there are 2 methods which are generally used. First is the H refinement and the other one is the P refinement. So to understand how these 2 methods vary, let us look at this model which is already meshed. So if I want to refine this mesh using a H refinement method, then I would just directly increase the number of elements in this grid. More the number of elements, more would be the number of calculations over a short distances, and thus the result I would obtain in this new mesh would be more accurate. If I want to refine the same mesh using P refinement method, then instead of adding new elements, one can also increase the number of nodes in the mesh. While running any FEA simulation, the various displacement values are interpolated using some functions which are known as shape functions. So by increasing the number of nodes, you increase the order of these shapes. Higher the order, more accurate is the result of the simulation. Now we will take a look at the types of analysis that are available in the SOLIDWORKS software. We will just be giving a brief explanation here, and in the further sessions we will go into a bit more detail. So the first one is the static analysis. As the name suggests, static analysis is used in places where the forces, load, acceleration and many other initial conditions which are applied do not vary with time. So as long as the constant load is applied, static analysis can be used to check the stress, strains or displacement in various models subjected to various forces. The cantilever beam, for example, which we saw at the beginning, would be an example of static analysis. Then the next type is the fatigue analysis. This applies for machines or components which are subjected to loads regularly after fixed intervals of time. When a material is subjected to loads again and again for long duration, then the material becomes weak and usually fails at stresses lower than its ultimate tensile strength. So to deal with such situations where you would like to know how long the component will last, one can use a fatigue analysis. Next is frequency analysis. Whenever any object is subjected to any force, there is vibration in the object, and every object vibrates at a fixed natural frequency. In certain types of problems, which we will look into in further sessions, it becomes important to know what the natural frequency of the object is. So to find the natural frequency of any model, frequency analysis can be used. Then we have the buckling analysis. Buckling is a type of material failure which usually occurs when long members are subjected to compressive loads. If you have a vertical column fixed at both ends and you keep increasing the load, there is a chance that after a specific value you will notice a sudden change in the shape as shown in the image. So buckling analysis, you can visualize this process and check the load values at which the buckling would occur. And in the end we have drop test. As the name suggests, this type of analysis is used for checking the impact on any component if it is dropped from a certain height and velocity. This is usually used for electronic components and gadgets such as mobile phones. So after running this analysis, you can check which places on the object are subjected to more stress, and you can make the design changes accordingly. So that's it for this session. So let's have a quick summary. So in this session, we saw the various methods of solving engineering problems such as analytical, experimental, and numerical methods. We learned about the general steps in FEA, which are pre-processing, processing, and post-processing. Then we saw what is meshing and how to refine it. And in the end, we saw the various types of analysis that can be performed in SOLIDWORKS. Welcome to another session in our course, FEA using SOLIDWORKS. So before moving on to the coursework, let's have a brief look at the content that we will be covering in it. So in this session, we will be discussing what a structural analysis is, and then we will move on to discuss what a static analysis is. We will also discuss on how it is different from a dynamic analysis. We will then see what a linear and non-linear analysis are, and also where to use them. So the first topic is structural analysis. Here the word structure doesn't just refer to the civil structures such as bridges and buildings, but also to mechanical components of all types. It can include gears, bolts, pistons, etc. Under working conditions, these components undergo numerous types of loads and forces. So to understand the different stress and strain experienced by these mechanical components, we perform a finite element analysis. By performing FEA, we are able to get the displacement values of the components under loads, and through that we can get the other derived quantities such as stress and strain. In the previous session, we had seen that there are many special types of analysis such as buckling, fatigue, and drop test. These special types of analysis were created for a few specific types of tests. We have special modules in SOLIDWORKS to perform them. But for any other general structural applications, we will be mainly using either static analysis or dynamic analysis, depending on the type of study. In the static analysis, we will assume that the forces that act upon the model are quasi-static, which means that the load is acted upon the model, increases very slowly, and thus the acceleration and velocity can be neglected. While on the other hand, in dynamic analysis, the inertial and damping force are considered while we solve the acceleration and velocity of the components. This is done before we find out the stress and strain. In static analysis, when we start a simulation at point A, we get an end result at B. Because of this fixed delivery of results, any data or analysis between the points A and B cannot be relied upon. Only the end result can be used to make a meaningful conclusion. But in the dynamic analysis, the intermediate results which we get at each step of the analysis are reliable and can be used. In short, we can summarize the differences between the two as: a static analysis can only be performed upon two conditions. The system being simulated does not depend on time, and the loads being applied on the system is constant. A good example for static analysis would be the simulation of a load on a chair. Whereas in dynamic analysis, the system, the load applied, or both might change with time. A good example for dynamic would be the simulation of a spring's compression. So depending upon the requirement, one may choose to go with either static or dynamic analysis. Both static and dynamic analysis have two subtypes available: the linear and non-linear analysis. An assumption is made that there is a linear relationship between the stress and the strain in the model throughout the simulation. But once the material crosses the yield strength value, its stiffness starts changing. So in order to capture the non-linear effects, the solver goes back to the material and evaluates the stiffness before proceeding on to the next step. So to capture the non-linear effects, we have to perform the non-linear analysis. Since the stress strain vary linearly in the linear analysis, it could also be said that linear analysis obeys the Hooke's law, which states that the strain in a solid is proportional to the amount of stress applied, and the deformations in the linear analysis are not very low, whereas the non-linear analysis, there could be large deformations in the model which are not proportional to the load applied on it. The primary places where we will be using linear analysis is when we know that the forces on the components do not change in direction or magnitude. It is also used when we are trying to simulate one component within a large assembly. A good example would be simulating a bolt in an off-road car. We know that the vehicle will be under a lot of stress and also will experience a lot of forces from multiple directions. And our goal here is to just see how this specific bolt fares under all these conditions and not the entire vehicle. Another place where linear analysis is used is when we don't really expect the component to move much. The last major assumption, that is, which we are simulating, does not go beyond its yield strength. So in this case, where exactly we'll be using a nonlinear analysis? So let's consider an example of a cantilever beam. The beam has a certain dimension of x, y, z, and we apply the force of 100 Newton on the top portion of the beam. This causes a deflection in the beam. The developed stress is well within the yield strength of the beam, so all is good. This is a perfect example of linear analysis. So let's consider a second example. It's a similar beam, but with a different approach and design. When you apply a certain load on the top side of the beam, you will notice that after a certain amount of deflection, the bottom part of the beam will get in contact with the support bracket, which is over here. That in turn will change the overall output of the simulation, because here we are not just performing a simulation of the cantilever, but also the bracket which holds the beam. So because of the deflections in the beam, the bracket will also have deflections. In such situations where the contact point in a system changes in the course of the simulation, we tend to use a nonlinear approach. If we solve this example using linear approach, then the contact points will not update properly and end up with bad results. So in such cases, we will be considering a nonlinear approach instead of a linear approach. Now that we have cleared the cloud on where we will be using linear and nonlinear analysis, let's now talk about the different reasons due to which nonlinearity is in a material. So the first reason is geometric nonlinearity. When the stiffness of the material changes due to change in the shape of the model, then it is termed as geometric nonlinearity. This can occur due to an element undergoing very large displacement or rotation. So in such cases, we will have to go for a nonlinear analysis to get accurate results. In SOLIDWORKS, even if you go for a linear analysis and if the software detects any large deflections during the course of the simulation, you will be notified about it and will be given an option to switch to nonlinear analysis to get an accurate result. Other than geometric nonlinearity, we also have material nonlinearity. Material nonlinearity can occur due to two reasons. The first one is creep and the other one is elastic limit. In creep, if the material is acted upon by a load for a prolonged period of time, its stiffness does not remain constant. Instead, it starts varying with time. Hence, we need to perform nonlinear analysis on such cases. Secondly, beyond the elastic limit, any metal would move into a nonlinear region, while the non-metals can behave non-linearly within the elastic limit. To help you better understand the two types of non-linearities, we'll do a comparative study of a model. Just notice we have already run the simulations in the SOLIDWORKS software and we'll be just showing the final result to you. First, let's take the model of this metal plate with a hole in it, and we'll apply a force of 300 kilonewtons on one end while the other end is fixed. We'll run both linear and non-linear analysis on this model. Both the results will have stark differences between them. In the left, you will have the linear analysis, and on the right, it is the non-linear analysis. If you look at the results on the right hand side of the results, you'll notice a red arrow mark. It is to denote that the applied force has caused the metal plate to cross the yield strength and get into the plastic region. In the plastic region, the stress-strain relation is not linear. Because of this, the amount of deformation and stress developed in the metal is much lesser than the linear assumption taken in the linear analysis. Because of this, we cannot consider the results of linear analysis in this condition. Apart from geometric and material nonlinearities, we also have the contact nonlinearity, which is caused by changing status of contact throughout the simulation. We have already discussed the contact nonlinearity in the video a few minutes ago. The cantilever beam with the support bracket is a perfect example for contact nonlinearity. So let's have a summary of the things that we've learned in this video. In this video, we learned what is static analysis and where we use it. And we've also seen what a dynamic analysis is and what the difference between static and dynamic analysis is. We then proceeded on to the types of static and dynamic analysis. We talked about what a linear analysis is and what a nonlinear analysis is. We discussed the difference between linear analysis and nonlinear analysis. In the end, we discussed the various types of nonlinearities. Well, that's it for this video, guys. In the next video, we will be showing you how to transition from the modeling environment in the SOLIDWORKS and into the simulation environment. In the previous session, we looked at some of the types of analysis that could be performed in SOLIDWORKS, such as static, dynamic, linear, nonlinear analysis, and much more. In this session, we will be introducing you to the SOLIDWORKS 2019 simulation environment. The video is made with the assumption that you are already familiar with 3D modeling suite in SOLIDWORKS. So without further ado, let's just get started. So as you can see right now, I have opened my screen into the SOLIDWORKS environment. So if you are not sure how this comes, all you need to do is double click on the SOLIDWORKS icon that you will have on your desktop once you install the software. Or if you don't have the icon on your desktop, you can just go to the search bar and type SOLIDWORKS just like this. So I got this by pressing the Windows key here. So you can now type in SOLIDWORKS just as I did here. Click on this one and you will get this interface. Once the software has loaded, you will either be met with a welcome tab or a plain screen. So since we don't have anything on our interface right now, I'll just go ahead and press on Ctrl+N, and this gives us the new SOLIDWORKS document dialog box. So from here you can either select part, assembly, or drawing based on your requirement. Since we will be working on a part model, I'll just click on part, and I'm not pressing OK because there's something else I need to show you. Let me just press cancel. For now, what I'm going to do is I've already created a model just for the sake of this video. So I'll just directly open into it. So I'll press Ctrl+O. Now I'll just navigate to the model and press open. This will open the handle solid part that I've already made. So we have it. Let me just maximize this one. As you can see, I have activated the view for the front plane, top plane, right plane, and also the origin. On top of that, I've also defined the material for this handle. So let's have a quick recap of the commands that we have in 3D modeling module in SOLIDWORKS. Most of you should be aware of the options available, but there is no harm in having a small recap. The first and most important thing in any 3D modeling software is to have consistency in the units that we use. So to select the type of units we'll be using, we can go to the unit system drop-down box in the bottom right-hand corner of the screen and click on this. Here we will get the different types of unit systems that are available. For example, the first one is MKS, meters, kilogram, second, CGS, centimeter, gram, second, or mmgs, millimeter, gram, second, and the IPS, which means inch, pound, and second. Or if you want to customize the unit system, you can just go to edit document units and customize it from there. The next important thing, the planes and the origin. There are three different planes in which we can do our 3D modeling in SOLIDWORKS. They are the XY, YZ, and ZX. These planes are also known as the front plane, top plane, and the right plane respectively. By default, they're actually hidden. But right now in this model, what I've done is I've just activated the view for them. To do this, you just need to select on the plane, right click, and press on the eye icon. So if you want to hide it, press on the hide option, and that the plane will be hidden. And if you want to view the plane, you just need to right click and click on show. Here you can also select the type of material you want your model to have by right clicking on the material option in the design tree. In the entirety of the course, we will be primarily discussing only three modules in the software. They are the features, sketch, and the simulations. As you can see, the simulations module is not visible. That's because we need to activate the license. So to do that, we need to go to SOLIDWORKS add-ins and press on SOLIDWORKS Simulations. So once we press it, what happens is the software will cross-verify with the licensing server to check whether we have the SOLIDWORKS simulation package with us. So if you have not purchased the SOLIDWORKS simulation package, this option will not be available. So since we have it, you can see that this extra module has appeared. So to access it, you just need to click on it. So before moving on to simulation, let's just discuss about the rest of the modules. What's the difference between all three of these modules? We'll first talk about the sketch module. Let's go ahead and click the sketch module. The sketch module is used to draw 2D diagrams of the objects which we use as a basis to model our 3D objects. In the sketch module, we have many options to generate 2D shapes like the circle option, the rectangle option, the polygon option, the line option, and many more. The next module is the features module. Here we can create 3D models based on our 2D inputs. Here we have options like extrude, revolve, sweep, loft, extruded cut, revolve cut, fillet, and many more. I've already created the 3D model, just as I said. So this is just a 3D model of a handle which we use to pull or close our doors. So what we will be doing is we'll just be trying to simulate the action of someone pulling the handle of the door. So to do this, let's just head over to our simulation environment. I'll just click on the simulation option and I'll press on new study. This will change the user interface on the left side of the screen. Here, the property manager will replace the design tree. It will also ask you what type of simulation you would like to perform on the model. Let's go ahead and press on static. Let's name it as handle static. And let's go ahead and click on the OK option. Once we press the tick button, it will open the design tree. Since we have not assigned a material to our model, we will go ahead and do that now. Let's right click on the name of our model in the design tree. Since I have named it as handle, that will be the name here too. Right clicking on it, we will get a drop down box with many options. Two specific options are of importance for us. They are the apply or edit material option and the apply favorite material. The favorite material option allows us to select common materials such as plain carbon steel, cast alloy steel, brass, copper, nickel, rubber, etc. If the metal or material you are looking for is not present in the favorite materials option, you can go ahead and click on the apply or edit materials option. This will open the materials dialog box for us. Here we can select a wide range of metals and non-metals. All these materials have a predefined set of values derived from actual materials. And if you want to enter custom values for your metal or non-metal, you can do that by inputting your values in the custom plastics under the custom materials option. Here you can input values such as plastic modulus, Poisson's ratio, shear modulus, yield strength, and much more. Once we have selected the required material, we just need to press on apply and the selected material will be applied to our model here. I personally want to apply brass as the material for our handle. So let's go ahead and do that. So let me just close this dialog box right now. I'll just right click on the handle option, apply favorite material and click on brass. And brass has been applied. So as you can see, here next to the name of our model, you will have the name of the material that we have applied. Once we have defined the material, we can move to connections. Let's right click on the connections in the design tree. This will give us a dialog box. We can also add connections from the connections advisor option, which is available in the taskbar. Let's click on the small arrow here. From here, you can choose different types of connections that you would like to give to your model. Since this is a simple 3D model with no points for connections, none of the options are applicable to us here. Similar to connections, you can either click on the fixtures option in the design tree, or you can click on the small arrow below the fixtures advisor in the taskbar. So from this drop down, let's click on fixed geometry. If you have noticed these handles on doors, you would have observed that these handles are actually held into place on a door by help of screws or pins. So we will need to portray the same action here also. So what we will be doing is I'll be selecting these circles as fixed positions, because this is where we will be having our screw or pin. So since we have 4 holes, we will be selecting it 4 times. Let me just go ahead and do that right now. And it is important that you don't select the circle, you select the cylinder. Here, since ours is a fixed joint, we have selected the fixed geometry option. Similarly, if the model whichever you are simulating has a roller or slider or even a fixed hinge, you can select the appropriate option here. So let's click on OK. Our next course of action would be to give external loads for the geometry. For that, we can either right click on the external loads option here, or select the small arrow here from the external loads advisor option in the taskbar. So I'll just click on this one and I'll select force. So this will prompt us to mention where our handlebar will be experiencing force. As any common person would know, we will always pull our handle from the long cylinder here. But here you can notice that all the arrow marks in the depiction act inwards into the handle. But this is not how force acts on a handle. To avoid this, we can select the direction in which we want our force to be acting. So to do this, we need to select the Select Direction radio button. This will add a few more additional options in the property manager. To define the direction of force, select the pink rectangle. This allows us to determine the direction of force. Since we want our force to be perpendicular to the front plane, we will be selecting that. So I'll just go over to the front plane and select the front plane. Our next course of action would be to decide the direction of force with respect to the selected front plane. To do that, we need to go to the force option in the property manager. Here we will be having 3 options. The first one is force along the plane direction 1, force along the plane direction 2, and force normal to the plane. Since the third option is our required, we will be selecting that. As you can see, once we actually selected the third option, the direction of the arrows has changed to our required. Now let's input the value of force we would like to act on our model. Let's add a force value of around, say, 500 newtons. Now let's press on the green tick icon. Now we have successfully added the force, and also we have fixed our model. So our next course of action would be to mesh the model. To do that, we can go to the mesh option in the design tree. Here right click on mesh and press on create mesh. Here you can set the mesh density by sliding the slider along the direction. So if we move it towards the right, we'll get a finer mesh, and towards the left, we'll get a much coarser mesh. You can also set the mesh parameters by clicking on the mesh parameter option. Here, since this is actually a very simple simulation, we don't really need to change any options here. So we'll just make it a 5mm mesh. You can do that by changing it here. This option is to define the global size of the mesh, and this option is to define the tolerance of the mesh. If you have many curvature based element, you can select a curvature based mesh. Let's click on OK. Now the solver will be meshing our model. Here you can see that our model has been meshed. So all that is left for us is to run the study. Before I press on the run the study option, there is another thing which you need to know. Here in the mesh options, if you feel that your model is very simple and you don't really need to dab around with the mesh options, you can just select the mesh and run option. So once you press this option, the solver will automatically mesh the model and run the simulation. So let's do that. We'll just click on the run the study option to run our simulation. Okay, so the simulation has completed and we have our results. Here you can notice that the model has deformed a lot. If you think about it, we didn't add a lot of force to it either. It was just 500 newtons of it. If the model was made of, say, a weak plastic material, the deformation can be justified. But our model was made of brass, which is a metal. So what do you think went wrong? To get our answer, let's look at the top left corner of our workspace. Here you can see that the scale of deformation is around 626 times. Since the amount of force that we had input is less, the deflection and the change in the stress strain are also very less. So to make the results much more readable to the end user, the deformations are increased. So to get the original deformation scale, just double click on the box here. This will create a new stress plot option here. Here you can just go to the true scale radio button and press on OK. So once you press that, you can notice that the deformation scale has been reduced to 1 and your model has also changed. Here we can see that almost no deformation even takes place. And in the right side we have our contour legend. So this is a 1 Mrs. Stress legend. Well, that's it for the video, guys. If you feel that I've left out a lot of parts, don't worry. This is just an introduction video which is to set you in pace with the simulation environment. Here in this video, we've just performed a simple static analysis with a very small force. Now following videos, we will be taking a much more in-depth dive into the different types of FEA simulations that we can perform in SOLIDWORKS. I'll meet you in the next one. Bye. Back to another session of FEA using SOLIDWORKS. In the previous session, we took a look at the UI in the SOLIDWORKS software and also how to migrate from 3D modeling environment and also how to migrate from the 3D modeling environment and into the simulation environment. In this video, we will be discussing how to perform linear and non-linear static analysis. We will also be discussing how to perform a dynamic analysis. Along with this, we will be discussing how to perform FEA analysis using 2D simplification. So let's begin. Let's first create a model. A simple plate with a hole is a basic problem that any FEA engineer would start with while learning the software. So once I show you how to add initial parameters, we'll proceed to the analysis. So here I've opened the SOLIDWORKS window. I will click on New and select Part and click OK. As you can see, the software was opened into the part modeling interface. So our course of action here would be to create a simple plate. To do that, let's go to Sketch and click on the sketch icon. This will give us the 3 different planes. I'll select the top plane and it is changed on to top plane. Here I'll just select on the rectangle option, but instead of corner rectangle, I'll be selecting center rectangle. I'll select the mid plane and create a rectangle. Now using the smart dimensions, I'll set 50 millimeter as dimensions on both sides. So let's select this one and change it to 50 here. And the dimension on this side also will make it as 50. Okay, we have our plate, and let's click on the tick. Our next course of action would be to create a circle. So let's go to the circle option and select it. Now let's move to the midpoint here and create a circle. And we want our circle's diameter to be around 15 millimeters. Here, if you notice, it is actually radius and not diameter. To do that, you can either make it a 7.5 or you can go to Smart Dimensions directly and select it from here. And here we'll change it to 15. And it has become 15. Let's click OK. Now let's go to Features and extrude this. Here, let's give an extrude thickness of 5 millimeters. I'll just click on 5 and click OK. Okay, so we have our plate. Now our work will be to perform a simple static analysis. To do that, we need to go to the simulation module, but as you can see, it is missing here. As I've just shown you in the previous video, we just go to SOLIDWORKS add-ins and click on the SOLIDWORKS simulation icon here. This will activate the license. What the software will do is will check in the licensing server and see whether we have bought the SOLIDWORKS simulation, and if at all we have bought it, it will show it. If it is not here, it won't come. So let's go ahead and click on simulation and click on new study. Since we're doing a static study, we'll select this one. It is actually selected by default, so no need to select it. I'll change it to static plate and click OK. Now the left side design tree has changed into the simulation design tree. Our first work would be to assign a material to this model. To do this, right click on part 1 and select apply or edit material. Here we have a list of all the materials which the software took from the database of SOLIDWORKS. Here we'll be selecting the default alloy steel, and here you can see all the different properties of alloy steel are mentioned, like elastic modulus, Poisson's ratio, shear modulus, mass density, tensile strength, compressive strength, and many more. Let's hit on apply and let's press close. Our next work would be to give fixtures here. Let's go ahead and press on fix geometry, and we'll fix this side and press OK. Now I'll be selecting Control 7. Next we'll be giving the external loads. To do that, let's go to force. This is done by right clicking on external loads. Let's go to force. Here we need to select the phase in which we want our force to be acting. Since we are looking forward for a tensile force, I'll select on this side. And now I'll be reversing the direction by clicking on this checkbox. If we don't reverse the direction, the force will be acting inwards. That's not what we want. We want a tensile. If it acts inwards, it will be a compressive. If it acts outward, it is tensile. So I'll just reverse the direction and I'll give 1000 newtons of force. And I'll press OK. Now our next work would be to mesh the model. So to do that, let's right click and select create mesh. We'll give the default mesh here and select OK. Okay, so we have our meshed model. This is a very simple analysis, so we're not giving much emphasis on the quality of the mesh or what type of mesh we are using. Let's press on run the study to run our study. As I said, it is done. Here you can see that we have got quite a colorful model as result, and the deformation is also very high. The high deformation is due to the deformation scale, which we can see in the top left corner. We have already talked about this in our previous video. The different stress values in the legend correspond to the different colors in the model. At the bottom, we can also see the yield strength value of the metal. And we will also notice that the stress value in the models are well below the yield strength value. Since all stresses are within the linear region of the stress strain graph, This analysis has given us acceptable results. Now you can also notice that the stresses right now are in the order of 7, 6 and 5. I will be increasing the force by a factor of 10. To increase the force, we can just right click on the external loads and click on the edit definition option. Here let's add another 0. So this becomes 10,000 newtons or 10 kilonewtons, and let's press OK. Since we've changed the input parameters, you can see that there is a small yellow icon that appears next to the results option. That means that some changes have been made to the parameters of the model. So we'll be running the study again. Let's click on run the study. Okay, so we've got our result. Now you can see that all the stress values have also increased by a factor of 10. But even now, the stress values are within the yield limit. Now let's increase the force by another factor of 10 and let's run the simulation again. Again, I'm going to be doing the same thing here. I'll just go to the force value which we have inputted, right click on it and select edit definition. Since it is now 10,000 newtons, I'll make it 100,000 newton or 100 kilonewton. I'll press OK and run the study. And we have our result, but this time you'll be able to see that there is an extra arrow mark in the legend here. So what happened here? Is that since we are using a linear analysis, the results are valid up to the yield point of the material. The arrow mark shows the point at which the yield strength of the material was exceeded, and thus all the results above the mark are not acceptable. We will have to run a nonlinear analysis to get realistic values from the simulation. So since we are performing a static linear analysis and the stress values which we had yielded are much higher than the yield strength value, then we should be switching to a nonlinear analysis to get reliable results. So let's do the same. Let's run a nonlinear analysis here. To do that, right click on the static plate name here and select create new simulation study. So to create a new study, we'll go to static plate and select the option copy study. Here under the target study, we'll select nonlinear and we'll select OK. Now let's run the analysis. Here, when we run the simulation, you can notice that the solver is taking much more time to compute this compared to the linear static analysis. And now we have the correct values for the stress. Here you can notice that the stress values in the nonlinear analysis are much lower than the linear analysis. To understand this much better, let's take a look at the stress strain plot of a metal. Now that we have the stress strain graph of a metal in front of us, here you can notice that the value increases linearly in the initial phases and then it decreases, and the rate of increment reduces after a certain period of time. And this is what is happening in the nonlinear analysis. As the amount of force that is acting on this phase increases, the total amount of stress that is developed in the metal also increases. Once the stress value crosses the yield strength, the rate at which the stress value increases starts to fall down. That's why you'll see that the stress values in nonlinear analysis are much lower than the ones in linear analysis. Now that we have a fair understanding between the linear and nonlinear FEA analysis, let's consider another example. Here we will first run a static analysis on a beam and then increase the load to check what happens when nonlinearity occurs. Okay, so I have the new window here. So what I'll be doing is I'll be making a cantilever beam. So let me go to features. I'll be selecting sketch. We need the right plane here. So let me select the right plane. And using the centered rectangle option, I'll make a rectangle. Now the dimensions will be 50 millimeters versus 50 millimeters. It will be a square of 50 millimeters. So I'll change it to 50 here and 50 here. Now next we'll be extruding it. We can directly press extrude, and I'll extrude it to a distance of 1000 millimeters or 1 meter, and let's press OK. Control 7. Okay, so this is the total length of our cantilever beam. Let's go to simulation, new study, and we'll be doing a static analysis. So I'll name it a static beam, and I'll press OK. We'll be doing much similar things that we did for the plate. So I'll just give a material to it. I'll give apply or edit material. Select alloy steel, apply, the color changed. Let's close it. We'll be fixing it. Let's go to fix geometry. Since for a cantilever beam, one face is always fixed. I'll fix this face and I'll press OK. Now we'll be giving it external loads. Let's go to force. So what we want to do here is we'll be giving 500 newtons of force on this edge, and you can notice that the direction of force is actually in this direction, so that is not our desired one. So to do that, we'll give selected direction and we'll select on this face and we'll reverse the direction. So what we've effectively done is we've selected the edge here, we selected the face at which we want force to be acting in this place, and we selected the direction or the plane along which we want our force to be applied, and then we reversed it. Now I'll input the amount of force, that is 500 Newton, and I'll press OK. Now we will go ahead and mesh the model. Let's go to mesh, right click and hit mesh and run. Since this is a very simple model, we don't really need to worry ourselves with the intricacies of meshing. So I'll just select mesh and run. Okay, so we have a cantilever beam with a little bit of deflection here. Now I'll be increasing the amount of load by another factor of 100. So I'll go to force, right click, edit definition, and let's make it 50,000 newtons or 50 kilonewton. Let's press OK and let's run this study now. Okay, so we have an error here. So what has happened here is that the software has detected a large displacement, and hence it is prompting us to switch over to a nonlinear analysis to get reliable results. So if we click on yes, the software will run it again in nonlinear analysis. Okay, so now that we have our results here, you can see that here we have the same red arrow as we had in our previous analysis. So that is again to indicate that the stress value has crossed the ultimate yield strength and that it is in the nonlinear region. Now that we have had a few examples on static linear and static nonlinear analysis, now we will be switching over to dynamic analysis. And in dynamic analysis, we will specifically looking into how to use 2D simplification. So what is 2D simplification? So it is just an option which can be used to reduce the computational time for models which are symmetric about a particular axis. So before we start, I'll just explain you what we are trying to do here. It's pretty straightforward. We have a die, we have a punch, and we have a sheet metal. So the punch is moving into the die to deform the sheet metal into the required shape. Our main objective here is to check the stress and strain values that are developed in the sheet metal during the punching action. So to get them, we will be required to perform a nonlinear dynamic simulation to get accurate results. So let's go ahead and do that. Let's click on New Study. Here we will be selecting nonlinear. Under that we will be selecting dynamic. Here you can see that by default it is selected as static. So let's go ahead and select dynamic. And here we will be clicking on the Use 2D Simplification checkbox. And let's go ahead and rename our model. We'll make it as nonlinear punch and click OK. Once you click OK, so the software will ask you to define a plane along which we have symmetry in the model. So for our model, it is symmetric along the front plane. So I'll just go ahead and click on the front plane. And I will select the depth here as 0.015. Here the 0.015 is the thickness up to which we need to replicate the 2D results to get the 3D object. Once we do this, we can see that we have the 3D representation of our model. So I'll just go ahead and press OK. So here you can see that our 3D model has been converted into a 2D. I'll just go ahead and press 7, Control 7. And our first objective here is to apply materials to each one of those parts. Instead of applying material individually to individual parts, I'll just go to parts and hit the apply material to all option. Here I'll select the default alloy steel, hit apply, and I'll hit close. Now we will be fixing the die here. So I'll go to fixtures, select fixed geometry, and I'll select this. I'll select the 3 sides of the die along with the 2 corner edges of the sheet metal. So this is done to ensure that the sheet metal does not slide off once the punching action takes place. So I'll just select them and click on OK. Here you can see the fixed portions of the model with the green arrow marks. Now that we've fixed all the required parts, our next course of action would be to define the direction in which our punch will be moving. So to do that, let's go to fixtures again, right click on fixtures and select the fixed geometry option. Here expand the advanced option, and here let's go ahead and select the top portion of the punch, and we're selecting the top portion to define the direction along which the force will be acting here. And here in the front plane, here the reference plane has automatically been selected as the front plane, and here we'll be selecting the long plane direction too. You can notice that the arrow marks here are all upwards, and that's not the direction in which our punch will be moving. To reverse the direction, we'll just click on the reverse direction checkbox, and our punch will be moving for 10 millimeters. So I'll just enter the value. You can see that the direction of the arrow marks has changed to our desired direction. Now below the translation, you can see the variation with time option. So if I click on curve and click on view, you will see how load or transition will vary in this problem. On the x-axis we have the time, and on the y-axis we have the translation. So here we can see that initially at 0 seconds, the translation will be 0 and the die will translate linearly with time. So at 0.5 seconds, the die will move a distance of 5 mm, and at the end of 1 second, it will complete the translation of 10 millimeters. The value of translations are negative because the die will be moving in the downwards direction. Now, if we want to change this, there is also an edit option available. Let me just go ahead and select it. Here on the first column we have the time, and on the select second column we can give either load or transition. So currently we have 0 load at 0 second and 1 load at 1 second. Also, instead of user defined, I can change it to unloading type. In this case, the maximum load will be applied at 0 seconds, and then it will be gradually unloaded from the material. And after that we have the loading unloading type of graph. So I'll just press on view so that we can have a much bigger view of it. So here we can see that the load will first increase and hit a peak at around 0.5 seconds, then it will start decreasing. So we can use all these settings based on our requirements. For now, I'll keep the default settings, which is user defined, and I'll click on OK. So when we run the simulation, the punch will be moving down 10 millimeters. So let's go ahead and run the simulation. Okay, I just got an error, so I just reset it and I was trying to find what the error actually was. So I managed to find what it was. I'm not editing it out because this is some small rookie mistake which majority of us make. So I'll just explain it to you. Let's go to reference geometry here and I'll select edit definition. Here, once we scroll down, you can notice that instead of inputting our value in millimeters, we've input into centimeters. So what happens is our die, even though the entire distance is much lesser than 30 millimeters, it was trying to move much far beyond it. So the solver had detected that it is not possible because of the contact sets, that it is not possible for this punch to move beyond the die. So it gave me an error. I was just banging my head and wondering where the error was, so I managed to find it out. So let's change it to millimeters and we will make it into 10 millimeters and select OK. Let's now run our simulation again. Okay, nice. We have our results here. Let's take a look at our results. Since we didn't define proper contacts before running the simulation, we can see that the punch is penetrating the sheet metal and the sheet metal is penetrating the die. So let's go and define proper contacts now. So to do that, we need to right click on component contacts and select contact set. Here we have faces, edges, vertices for set 1, faces, edges, vertices for set 2. So in the blue box, we'll be giving the 3 edges which will touch our sheet metal, and in the target box, we will select the one edge of the sheet metal which will touch the punch. And if you want to give friction, you can just go ahead and select it. Please ignore the stress value, it's just a small visual bug in SolidWorks, just pops up sometimes. And let's select OK. And we also have another contact set remaining, the one between the sheet metal and the die. So let's go ahead and set that. Go to component contacts, right click, select contact set. Here we will be selecting the bottom edge of the sheet metal, and in the target we'll be selecting all the edges which are in contact and which will come in contact. So I'll just go ahead and select all those ones. Again, ensure that you only select the edges and not the faces. If you do select faces, we will end up with a failed simulation. And select OK. Alright. Now that we've set all the required contacts and fixed all the parts properly, let's run the simulation now. So the simulation is complete. Here you can notice that we don't have any unrealistic interpenetrations. And you can also take the look. Here we have 3 types of results right now. One is the stress, displacement and the strain. Double click on the displacement. This shows you how much a specific body has moved. For example, if you look at the die, it's all in red. That means it is moved 10 millimeters. And we have the strain and we have the stress. You can also animate the movement. Let's go to displacement, for example. Select right click on the text and select the option animate. Wait for it to generate the frames. And once all the frames are generated, you can just increase the speed, decrease the speed, do whatever you want. You can also save it as an AVI file. To do that, you just need to stop the animation again, hit the save as AVI file, choose a location and again run it. So it will just compile all the frames and save it into an AVI file separately. I'll just go ahead and cancel it. So if you want to look at the 3D plot of this simulation, you can right click on any of the simulation results and select the show as 3D plot option, and it will generate the same 2D element into a 3D element for us. And we can also get the animation for the 3D die moving up and down the same manner in which we get the animation for this 2D die. And that is how we perform a 2D simplification, nonlinear dynamic analysis on a 3D model. By doing a 2D simplification, we are able to reduce the computational effort required to run the simulation and also get accurate results. Before we end the video, there is one another point that I would like to add here. Along with the material selection, which defines all the material properties, we can also specify a model type to get an accurate output. For example, let me go to the plate example we just did. Let's minimize this and maximize this one. And static. If we consider this plate which is being deformed in this study, this plate is actually behaving like an elastic material. This means that if we remove the force on the plate, then it will move back to its original position, which is not very realistic, as the deformation here is plastic and not elastic. So in order to get a proper output, we have to define a model type which lines up with the material we are using. To provide the correct type of material, we will be required to define it in the materials dialog box. So let's go ahead and do that now. Here, let's right click on any of our models and select apply or edit material. Here in this material dialog box, click on the model type drop down box. Here we will be provided with a list of material types which we can choose depending upon our requirement. Let's discuss what each of them mean and denote. The first and the default option would be linear elastic isotropic. In this option, the material properties are assumed to be constant in all the planes. On loading, the materials will experience deformation and regain its shape back upon unloading without any plastic deformation. The second option is linear elastic orthotropic. In this material type, the user will have to define the material properties along the x and y direction in order to perform the simulation. This is because orthographic materials exhibit different material properties in different directions. Here the material will also revert back to its original position once the loads are removed. While choosing this option, we will have to give the elastic modulus of the material in the y and z directions, along with the Poisson's ratio in all the planes. Since the values are all great, we will have to copy all the values from the tabulation and paste them in the custom materials option to proceed on. The next one is the nonlinear elastic. Here the model is assumed to have nonlinear behavior, but the deformations are still elastic. After this, we have plasticity one misses. In this model type, it is assumed that the material's yielding will occur when the one misses stress equals the yield stress of the value. This model is very accurate for ductile materials. Apart from plasticity one misses stress, we have two other models. They are plasticity Tresca and plasticity Drucker-Prager. In plasticity Tresca, it is assumed that the yielding will occur when the shear stress in the model is half the yield stress that is obtained in a simple tension test. In Drucker-Prager model, the yielding is based on the calculations based on the Drucker-Prager yielding criterion. The Tresca and Drucker-Prager models are a bit too complex for a beginner. These two models are developed over the von Mises model and are used only in a few special applications. The next ones are hyperelastic models. Hyperelastic models are used to describe the materials that can undergo large amounts of strain and displacement under small amounts of stress and load. These are generally used to model components made of rubber and other similar materials. The assumption made here is that the material is non-linear, isotropic, and elastic. The next one is viscoelastic. This is used to denote materials which exhibit viscoelasticity. If you're not sure what viscoelasticity is, it is a property of a few materials which can exhibit both viscous and elastic characteristics when undergoing deformations. A good example for this are synthetic polymers, wood, human tissue, as well as metals at very high temperatures. So as we can see, each of these material types can be used to simulate different types of material properties. So before we conclude this video, let's have a quick summary of all the concepts we looked in this video. So we first discussed on how to perform a linear static analysis. We then looked into non-linear static analysis. We also performed a dynamic non-linear simulation. We discussed 2D simplification and talked about contact sets. We then concluded the video with a discussion about different material types that can be assigned in SOLIDWORKS. Well, that's it for this video, guys. We'll meet you again in the next one. Welcome back to another session in the course FEA using SOLIDWORKS. In the previous session, we had performed a simple static and dynamic analysis. In this session, we will be performing a 1D, 2D and 3D FEA analysis on a uniformly loaded cantilever beam. You see, FEA analysis is classified into 1D, 2D and 3D analysis depending on the type of elements we will be using. But what are these elements? We had previously seen how models are discretized into splitting it into multiple elements, and depending upon the shape and type of the models, different types of elements are used for discretization. The simplest element which we can have is a line connecting two nodes. This can either be a straight or curved line. So whenever we have a line as an element, it is considered as a 1D element. The image that you are seeing on your screen is a 1D mesh of a simple cantilever beam in SOLIDWORKS. Here, the cuboid beam is simplified into a single line and is discretized into many parts. If we discretize using surface elements such as triangles or rectangles, then it is considered as a 2D element. 2D meshing is generally done in SOLIDWORKS using the shell option. The image shown on your screen is a 2D mesh of the same beam which we used for 1D meshing. And if we use solids like tetrahedrons or cuboids for discretization, it is considered as a 3D element. These elements are used to discretize 3D models and mesh them. We shall look into each of these types individually. The first one is 1D analysis. 1D analysis is used when one of the dimensions of the geometry for which we are performing FEA is significantly larger than the other dimension. An example for this would be, let's say I have a long uniform beam and I am interested in looking at deformation caused by bending. Since the beam is long enough, 1D elements are sufficient to produce the required result. Going for 1D analysis instead of 3D, in this case would give an accurate result and also reduce the computational time required. 1D analysis can be used for structures such as beams, bars, rods, pipes, etc., in which one dimension is significantly larger than the other two. After this, we have the 2D analysis. This is usually performed when two dimensions of the geometry are significantly bigger than the third one. Examples for this are sheet metals and plastic components such as instrument panels. So if you want to perform an FEA analysis on a sheet metal, then instead of using 3D cuboids, you can get a result of high accuracy by just using 2D sheet elements, which are called as shell elements. Using 2D elements instead of 3D elements will reduce the computational time required. And after this, we have the 3D analysis. We will use this when any one dimension is not significantly greater or smaller than the other ones. Using 3D elements would also give you the most accurate result, but it would also increase the computational time required. Now we will be doing FEA analysis of a cantilever beam using 1D, 2D and 3D elements. I had explained that since a beam is a structure with one dimension significantly larger than the others, doing 1D analysis would provide us with accurate results. So now we will actually perform the analysis and see how much the value differs by solving the same problem in different ways. So I have the SolidWorks interface open here. So let me press Ctrl plus N. This will give us a new SolidWorks document. Here I'll go ahead and double click on part. This should give us the part interface. Okay, so we'll start with the sketch screen. Here let me click on sketch and I'll select the right plane. And from this I'll select a center rectangle and make a rough rectangle from the center. Now let me just go to smart dimensions, and here we are making a square cantilever beam, and our square has a dimension of 30 millimeters on both sides. So I'll just add the same values there. So I'll mark this one side as 30 and press OK. I'll do the same for the other side also. It's 30 and OK. And I'll be directly going to features and give extrude, boss or base. And now I will extrude the sketch up to 500 millimeters. Click on OK. Okay, so we have our model here. Let's go into SOLIDWORKS add-ins and activate the simulation license. Okay, so simulation has gotten activated. Let me just go ahead and press on simulation option. And now I will select new study. And for now, we will be performing a static analysis. So I'll select static and make it a static 1D. And now I'll change it as static 3D. And I'll press OK. I'll right click on part and I'll apply the default alloy steel material, or you can always apply whichever material you would like when you're performing the simulation yourselves. We'll just wait for that dialog box to open. Okay, so we have our material dialog box open. Here I'll just select alloy steel and hit apply. Now let's just close it. And our next course of action would be to set the fixtures here. Select fixed geometry by right clicking on fixtures. Since this is a cantilever beam, only one side of the entire beam will be fixed. So I'll just select the left side of the beam and press OK. So I'll be fixing this side. I'll press Ctrl 7 to go to isometric view. Here our next action would be to give external loads to it. As I just previously said, this is a uniformly loaded cantilever beam. So the amount of load is uniformly distributed about a specific face. And we will be applying the force on the top face of this beam. So I'll just select the face and select 1000 newtons of force. That means 1 kilonewton. And the direction is correct, so we don't need to reverse it. It's downwards, and I'll press OK. Let's just hit mesh and run. Okay, so the solver has finished solving it, and the maximum one misses stress developed in the model is at this area, and it is about 5.459 into 10 power 7 Newton per meter square. We'll run another 2D and 1D analysis of this same beam, and we'll check how much stress we will be developing, and we'll just compare the other two. Okay, so to run a 1D analysis, we'll just go to model and hit on new study. From this, we'll change this. Instead of static 2, I'll make it a static 1D, and I'll let it be selected in static, and let's press OK. Let's apply the default alloy steel material, which we have applied for the previous one also. I'll just hit apply, and I'll be closing it. Now our next course of action would be to define this 3D beam as a beam element. So to do that, I'll just right click on part and select the treat as beam option. Now you can see that we have two separate nodes which appear over here. The meaning of this is that instead of it being a 3D beam element, we've just converted it into a 1D beam element. So our next work would be to set the fixtures here. Let's go to fixed geometry and select that one. Now I selected the joint and I'll press OK. And next we will be adding the forces. Here you cannot define forces to the faces. Since this is just a 1D element, we can't do faces because faces are 2D. To apply force to this model, you need to select on the beams option and then select the entire beam. And this way the solver will know where exactly you're giving the force. So since we are giving the force to the entire beam, we're just selecting the entire beam. So the next action would be to set the face along which we are applying the beam, applying the force. So the next option would be to set the direction along which we are applying the force. Here I'll select this edge and use this to define the direction. So I'll just give select on force and change it into say 1000. Since we gave 1000 newtons in our previous 3D analysis, 3D static study, we're going to give 1000 here also. And we'll check the direction. The arrow mark is actually pointing downwards, so this is fine. We don't need to reverse the direction, we just want it downwards only. I'll press OK. Now let's just mesh the model. Just click on create mesh. Okay, so here you can see that instead of having a 3D mesh, the solver has made a simple 1D mesh, and this will significantly reduce the computational time for us. Now I'll just select on run this study and let the solver do it. Okay, so study has finished and we have our results here. Now let's do a 2D analysis of the same model. So I'll go to model again and I'll select the new study. Instead of static 3, I'll change it into static 2D and I'll select OK. Here under parts, let's just apply the same alloy steel. I'll press apply and close. Here to define this entire beam as a 2D shell element, what we need to do is right click on part 1 and we need to select the option define shell by selected faces. I'll just go ahead and select it now. Now here you need to select a certain face on our 3D object. I'll be selecting the side face here, and here I'll input my value as 30 millimeters. Now the shell will be offset by a value. Now the face will be offset by a value of around 30 millimeters. I'll press on OK. Now we need to fix it. We need to fix geometry. In our previous one, we had a 3D element. We had a 3D cantilever beam which was moving up and down in the animation. Now we just have a simple sheet metal which is bending down and up. So this is to denote that this is taken as a shell element. So we're not going to give an entire face. We're just going to give this one edge because this edge is what we defined as a shell element. Select OK. And for external loads, we're doing the same. We're only selecting this one specific edge, and the direction would be downwards. So to set the direction, I need to select this vertex. I'll select on force. Okay, so the direction is by default selected as downwards. So we just need to define the value of force. We'll make it as 1000 newtons and select OK. Now we need to mesh the model. I'll select create mesh and we'll give the default one. So here you can see that our model is actually meshed and it is a 3D element instead of being, it is a 2D element instead of being a 3D element. Don't worry about these arrow marks. They should be along the entire length of the beam. This is just a small graphical glitch which occurs sometimes in SOLIDWORKS. It is actually defined for the entire length of the beam. Okay, so now that we have everything required, we'll just run the study now. Okay, so now that we have the results for our 2D analysis, let's go ahead and compare for all three of these analyses. So to do that, we just need to right click on results and select the compare results option. Here, you need to select the all studies in this configuration radio button. So once you select that, what happens is that the software will consider all the different results that we have obtained in each of these simulations. So we don't want to compare all of them. We'll just compare the displacements at the moment. So I'll select displacement in all of them. I'll checkbox them and I'll select OK. So here you can see that the screen has been split into 4 different places. So here we have the 3D model of the 2D simulation. So just ignore this part. And here we have our 3 different results. So the first one is our 3D analysis, the second one is the 2D analysis, and the third one is the 1D analysis. Here you can see that the maximum deflection in each of these is somewhat much similar to each other of them. So here it is 1.102 millimeters, here it is 1.103 millimeters, and here it is 1.107 millimeters. So this is how we perform a 1D, 2D and a 3D analysis. So to exit this, you just need to select the exit compare. I'll just go ahead and select this one. And we are back to our first analysis in these options. Well, that's it for this video. Let's have a quick summary of all the contents that we looked into in this video. Okay, so we're back to our PPT. So in the beginning, we looked into the different classifications of FEA. Then we discussed on what are 1D, 2D and 3D elements and where exactly we use 1D simulation, 2D simulation and 3D simulation. And we also performed a 1D, 2D and 3D simulation work of a uniformly loaded cantilever beam in our SOLIDWORKS simulation module. And in the end, we had a small comparison of our results. Well, that's it for this video, guys. Hope you have understood how to perform a 1D, 2D and 3D simulation. I'll meet you in the next one. Welcome to the next video in the course Finite Element Analysis using SOLIDWORKS. In our previous video, we had a look at the 1D, 2D and 3D simulations in SOLIDWORKS. We also had a comparison between the results of these three simulations that we performed. In this video, we will be talking about something called as the parametric study. In specific, we will be discussing what is a parametric study and why it is used. And we will also discuss on what are the advantages of parametric study, how to access parametric study in SOLIDWORKS, and also how to optimize a model using parametric study. And in the end of this video, we'll have a summary of all the topics that we've discussed. So without further ado, let's get started. The first question that we will be answering is, what is a parametric study? A parametric study allows you to nominate a parameter for evaluation by defining the parameter range and specifying the design constraints. Once this is done, the software will analyze the results of each parameter variation and give an optimal solution to our problem. The definition sounds a bit too complicated to understand. Yeah, I know that. So don't worry, we'll explain it with the help of an example. So let's assume we have a glass bottle of a certain dimension. The bottle holds, say, 250 ml of fluid. Now, the company that is manufacturing the bottle wants to increase the total volume of the bottle to, let's say, 350 milliliters, all the while keeping its diameter constant. So instead of running multiple trial and errors, a parametric study can be performed on the bottle. Here we can fix the required parameters like diameter, thickness of the material, shape, etc. and vary the total height of the bottle to arrive at the required capacity with minimal changes in the dimensions and shape. Because of the flexibility to change the parameters of components, parametric study can be a very versatile tool. Another advantage of parametric modeling is that the shape of the model geometry can be changed as soon as the parameters such as dimension or curvature are modified. Because of this, there is no need to redraw the model whenever a change needs to be made. This greatly saves time for engineers and especially in the design stage. With this option, we can also arrive at optimal dimension of a certain component for the required work. We'll get a much better idea of this concept once we proceed on with the software part. So let me open up SOLIDWORKS quickly. So here we have the SOLIDWORKS part interface. I've activated the front, top and the right planes. So what I will be doing is I'll just make a simple model and run a simple static analysis on it. And then we'll change the parameter based on the constraints and our goals. So let me just go on to sketch. Again, sketch. I'll press the top plane here. And since most of our models were cuboids, this time we'll go with a cylinder. So to make a cylinder, we need to first create a circle. So our circle will be of a radius of maybe 50 millimeters, and let's press tick. Okay, so this is made. Let me go back to extrude and we'll make it 100 through mid plane so that we get equal 50 mm on the top and 50 mm on the bottom. And let's press tick. Okay, so we have our cylinder over here, and let's now perform the simple static analysis on this. Since we don't have our simulation option activated here, we need to go into the add-ins and activate it from here. So once we press this, the simulation license will be added onto the software. It might take a bit of time based upon your system. So we have it now. Let's go press the new study and we will mark it as cylinder static background. Nice one there. So we have our cylinder here. Let's assign it a material. My favorite material. I'll just give brass over here, and you can see the color of the material has changed. And the fixtures will just give a fixed geometry. Control +7 to go back to isometric view. And the external load, let's give force on the top plane. I will be giving 50 kilonewtons, so that is 50,000 newtons. And let's press OK. Alright, so we have now given the force and also fixed the model. Let's go ahead and mesh it. Let's just first create mesh. We'll alter the mesh parameters and say that we wanted a 9 millimeters mesh. Nice. Our model is now meshed. Let's run this study now. So now you can see that based on the force, a little bit of deformation is occurring on the bottom side, and about 9.5 to 10 power 6 Newton per meter square of stress is being generated here. And another important thing is you can see that the stress values are much lesser than the yield strength. So that won't be a problem because we used a static analysis. If at all our result had a value which is more than the yield strength, then we would have needed to start with the nonlinear analysis. Now, this is the part where we will be moving on to parametric study. So let's right click on cylinder static. Now let's go do our parametric study. So to start a parametric study, what you do is go to cylinder static and give create new design study. So once you go into this design study option, you will be met with 3 separate options again. So the first option that you can see is called as variable. So variables are just values that allow you to be varied to get closer to your code. So let's say you have this cylinder, and you can vary the height of the cylinder, the material with which the cylinder is made, and also the mesh, the dimensions, and many more. You'll understand what this is, just hold on for a second. And the next one is constraint. So constraints are a sort of a limiting factor that will also affect your code. You can use constraints to set a range within which the part is acceptable. And the last one is goals. The goal is what we expect to get from this parametric study. So let me go and define a few variables at the moment. I've not added anything, so that's why just giving you a few dashes over here. Let's go to add parameter. And here you can see it is quite empty. So if we do is we're going to give model dimension, and here you can see that it is showing 100. So what 100 is, when I double click it, you can see that this value is being added. So in short, what it is doing is it's just importing a certain dimension into the tabular column, which I can rename it. So I'll be naming this one as height. So considering this is the height of this cylinder, so I'll be naming this as height and enter. And the next one we want to vary is diameter. So if you notice, you're not able to see the diameter. So that's just once more problem that we have this model, because we have not marked the diameter when we were designing it. So let's quickly go do that. I'll go to model, edit sketch, and 100. Just exit it. I don't want to change anything. Nice. So I'll just go back to design study again, add parameter. Here you can see the 100 is showing up. So you can do this if one of your dimension is not showing up. You can just go back to your model and define it in the sketch. Let's go add 100, and I'll say this is diameter. And the next one that we will be changing is the simulation. So in simulation, what we will be doing here is we will change the mesh of this model. For that, we need to go to the simulation tab. Here you can see that we have the mesh, global tolerance, global size. Yes, that's what's required. And that's the mesh. If you remember, we added the value as 9. So we'll just add that one here. And the next value we will be adding is the force. So the external, we'll just go to external loads, click the arrow mark, we'll get this one here. So we've given 50 kilonewtons, that is 50,000 newtons of it. So I'll just double click this one. Oh, see, we need to change it to simulation here. We have all our required ones. So let's quickly add these variables into the table. I'll just press force and then it is mesh. Okay, now that we have all our required variables, I'll just quickly tell you what each of these columns mean. So the last column here, it's called as step. So what step does is it will jump from the initial value to the final value. If we set the step value here as 10, then what will happen is initially the value will be 50, 60, 70, 80, 90. So we have defined a minimum and maximum range. So it will jump from 50 to 60, then 60 to 70. If I keep it as, let's say, I'll make it as 20. Make it as 20. Then what will happen is it'll run the test at 50 millimeters, then it'll jump to 70, then it'll jump to 90, then it'll jump to 110, so like that. So what we will be doing is we'll make it as 20, and the diameter also, let's make it 20. And force, you can see that our minimum value is 25 kilonewtons and the maximum value we have it as 75 kilonewtons. What we will be doing is I'll just show you discrete values. So what discrete value does is that it clubs all three columns and makes it into a single column. That means 50,000 Newton. That will be the force that is acting on the cylinder throughout the entire optimization study. So we will change it to range. That means the step will be eliminated and it will run it for 25, 26, 27 every single instant. And the next one is mesh. So we have given a 9 millimeter mesh. You can change the value to 5 and change it to 10, and the step will make it as 2 and make it 4 to have an even step. Okay, so we've given our variables. Let's move on to constraints. So what constraints does is it'll act like a limiting factor. As I explained, you'll get a better idea once we add a sensor to it. So under mass property, we don't need mass property. We'll go to factor of safety. And we'll add factor of safety. We don't want it to be maximum, we want it to be greater than 1. Okay. What constraint does is every single time a study is done for every single step, the software will ensure that the factor of safety of the output value is more than 1. So that is what minimum is. If you're going to keep it as less than, if your output value has a factor of safety of more than 1, the solver will not consider that. If you keep it as greater than, then the software will only take in values which have a factor of safety more than 1. So the next one we have here is goals. Let me go and add a sensor here. Here we have mass properties, and I'll go and click OK for this one. Once we've clicked the tick, we can see that the goal here is to minimize the mass. That means the optimal value which we obtain will be of the least amount of mass among these. You can actually check the mass here itself. 1 second. You can see that it is 785 grams. So now that we have everything set up, let's go run the study. We click the optimization option. Let's run this. So you can see that we have 15 different scenarios with which the study will take place. So the constraint that we've given is that the factor of safety must be more than 1. You'll see that the factor of safety here, it is 48, 48, 48, 7, and 47 here when the mass is changing. And the mass value, it is calculated based upon the diameter and the height. See, the height and diameter, everything changes. So let's wait for a few seconds. Let it run. So the design study is over, and you can see that the height and diameter 50-50, and the force is 25 kilonewtons, and the mass is 98.17477 grams. So based on the variable and the constraint that we have set, the solver has considered 15 different scenarios and given us an optimal value, all the while minimizing the mass of it. So initially we had somewhere around 700 grams of mass, and now the mass is just 98.17 grams. This is how a design study works. So the design study or the parametric study, this is just not limited to a simulation environment. You can also do parametric modeling with the help of this. So we talked about the glass bottle, right? We also showed this during the PPT. So we'll try to run the same scenario here. I'll just minimize this now. You need to hit File, Open Recent. Yes. So here we have the bottle which I was talking about. Let me give an isometric view. This revolve is not required, so I'll just suppress it by clicking this option. Okay, so now we have the clear bottle. To initiate a design study, we go to Evaluate and Design Study. So our main objective here was to increase the capacity of the bottle. So our variables which we have here are the radius and the total height of the bottle. I'll select this one, and I'm not going to give any explanations here because I've already talked about this stuff just a few seconds ago. Okay, we have that step here, and we're not giving any constraints. And our goal is to increase its volume. So here our volume is 246.64. That means it is somewhere around 250 milliliters. It's not to minimize, it's to exactly make it 350 ml, just like in the example. Okay. So both the height and the diameter will change. And I'll just run this study now. So the solver is telling us that there are a lot of scenarios for us to consider. So what we will do is I'll increase this to 10, and this should do the trick. Yes. Even with that, we have around 50 scenarios. We'll just wait for it to run it all. Okay, the solver has finished running the optimization study. It is telling us that a height of 350 millimeters and with a diameter of 48 millimeters, that is the closest one for our required volume. We could have gone a step further and also told it to minimize the mass of this bottle, but then again it will also add another scenario, and it would have easily gone above 75. So that's the end for this one. I hope you just got a good understanding of what exactly a parametric study is. In SOLIDWORKS it's called as a design study. So let's have a summary of all the topics that we had covered in this video. So in the beginning of the video, I explained what a parametric study is. After that, I explained the importance of a parametric study with the help of an example. We then discussed the advantages of a parametric study. After this, we performed a simple static analysis and optimized the model based on the constraint and goals we set. In the end, we also did a simple parametric modeling of a glass bottle. Well, that's it for this video, guys. I'll meet you again in the next one. Welcome back to the course FEA Analysis using SOLIDWORKS. In this video, we will be talking about buckling and buckling analysis. The topics we will be covering in this video are: what is buckling, the difference between bending and buckling, the relationship between buckling shape and the type of fixtures, performing a buckling analysis in SOLIDWORKS, and in the end, we'll just have a summary. So let's just move on with our first topic. What is buckling? Buckling is the sudden change in the shape of a component which is under a load. A good example for buckling is the bowing of a column which is under compression, or the wrinkling of a plate under shear stress. Buckling generally occurs when an object is subjected to a gradually increasing load. When the load reaches a critical level, then the member may suddenly change its shape and deform. The critical load at which the member buckles is called the Euler load. People often confuse between buckling and bending. Bending is generally a state of stress that is developed in an object due to the external force, whereas buckling is a state of instability, and the buckling failure is exclusive due to the instability of the slender member rather than the material deficiency. Bending generally occurs during the entire duration the load is applied, whereas that is not the case with buckling. Buckling occurs suddenly and only when the load reaches the Euler critical load. You can actually perform a simple experiment for this yourself. If you're still not quite sure as to what the difference between buckling and bending really is, you can perform a simple experiment for this. Let's take a slender steel scale. We'll fix it on two sides of a simple beam. Now place a small load. You'll notice that our scale is bent to a certain degree. As we keep adding the load, the scale continues to bend. Now let's do buckling. Let's position our scale in a vertical position like this and provide support to it so that it doesn't fall. Now let's start adding more and more load to it from the top. You can notice that initially the scale does not deflect, but after a certain load, it suddenly bends to the side. Why? Well, simple. It just reached the critical load of buckling. The buckling geometry of the material can also depend on the type of fixtures the member have. To prove this, we have an image. Here you can see that the four metal strips have different shapes of buckling. But why? It's because of the different fixtures each of these strips have. There are three types of fixtures being used on the metal strips. They are pinned, fixed, and free. A pinned end has a restraint on the translatory motion in all axes, but it is free to rotate about the axis in which it is pinned, whereas that is not the case with a fixed end. Fixed ends have restraints in all types of motion. They can't rotate, nor can they translate. The next one is a free end. Well, free ends are kind of self-explanatory. The column is free to move about any direction, and there are no restraints present in it. A good example for a free end column are the legs of a chair. Well, that's it for the theory part. Let's just move on to our software part. Okay, so what I have here is the SOLIDWORKS window. I've already opened the model in the assembly view. So this will be provided to you as an STL file when you're attempting the challenge. And what this model actually is this is a cyclonic separator, and this thing is actually resting on a support which has four legs. And what we will be doing right now in this simulation is to find whether these four legs will buckle or not. That's the objective of our simulation. Let's just start with it. I've already added the simulation license to the interface, so if you don't have it, you can just go into SOLIDWORKS add-in and you can press this one and you'll just get this one. And let's click new study, buckling, and you can just name it whichever you want. I'm just going to leave it with the default name. Let me click this deck. And before we proceed on with the simulation part, assigning material load and everything, there's one more thing that we need to do, and that is to suppress the unnecessary parts. This assembly is actually divided into 4 separate parts: the stand and 3 different parts of the cyclonic separator itself. For our simulation, these 3 are not required. But when you're running a simulation, you need to mesh every single component that is here. And this will only just increase the computational time, and also it'll just complicate the entire process a little bit. So I'll just suppress these 3 by, I'll just go to parts. I'll just control and select these 3. Exclude from analysis. You can either do this or go into the design tree and suppress them there. Okay, we have our stand here. So let's give our stand a material. Apply or edit material. Before I press apply, there's something which you need to know. You see, we have a few of the parameters in red color, a few in blue, and a few in black. And what it means is that the red values are very vital for this specific simulation. So if you don't have elastic modulus, since we're running a buckling analysis, elastic modulus, Poisson's ratio, and mass density are important. If you don't have these 3 values, you just can't run the simulation. The same way, if you run a static analysis or a dynamic analysis, every single time you open this material dialog box, you will be seeing that different values will be in the different color combination. And red means it is required. So if you don't have elastic modulus, you're not running the simulation. So I'll just press apply and press close. Okay, so you can see that this has changed color. And the fixtures, we'll just give a fixed geometry. Control 8. It's very important that you ensure that you give the proper points on the geometry fix, or else you'll just end up with wrong results, which we don't want that to happen. Let me just click another one over here. And Control 7, back to isometric view. And you can see that 4 of the ends have been fixed. External load will give a force. We will give a force on this face on the top, and 200 kilonewtons. So 200 kilonewtons is 1000 newtons. So 1, 2, 3. So we have 200,000 newtons of force acting directly downwards on this face. Don't need to select any directions, because the direction is actually, the assumed direction is correct, because this is downwards is how we want it, and downwards is how it is giving us. So before we move into meshing, there's something I need to tell you. These 4 legs is where majority of the deformation is going to take place. So to get much better results, what we can do is we can increase the refinement of the mesh on these 4 legs alone, and then add a much more coarse mesh on the top plate. That we can do it using the mesh control. So let me apply mesh control. Just take a little bit more time than normal, because you need to select individual faces and not the edges. Okay, we have selected all 4 of the legs, all faces of the legs, and we will give a 6mm mesh for all 4 of these legs. This is a very fine mesh. It will take a little bit of time, so let me just change it to 9. Let me just click the tick button, and now what we'll do is we'll just create a normal mesh. Nice, we have our mesh results here. You can see that the mesh size at the different parts is different. Here, this is a much more coarse mesh. Since we manually selected that we want the mesh in these parts to be much finer than the top plate, that's what it is. Now, since we have everything that is required, let's just run the simulation, run the study. It should take a little bit of time since the mesh here is very fine. Okay, we have the result here. Here you can see this is how the deformation of this support bracket will occur. You can actually have a look at the animation here. Click on animate and it should take place. It's creating the frames that are required for the animation, and here we have it. Increase the number of frames and just play along with that. Let's go back to isometric view, Control 7, and you can also save this. I've shown you how to do it in one of our previous videos. And another good part about this is you can actually generate a report of all your results in buckling analysis. If you go press report, it'll give you a dialog box, report options dialog box, and it'll ask you what are the values that you want in your report to be. The header information, who's the designer, which company does it belong to, the URL, the logo, the address, every single thing. You don't really have any information that needs to be input. I'll just give publish, show report on publish. So if you click this one, it'll just, once the report is generated, it'll show it to you. Let's publish. Yeah, so we have our report here. So here you can see the 3D model of our object, simulation of our symbol 4, the date at which this was done, the designer, the study's name, and what type of analysis this was. And you just get pretty much everything. The original model with the Skill-Lync separator and everything, the model which we analyzed, excluding the Skill-Lync separator, information of the model, and all the other required values. This can have a, once you run your simulation, you can just do this and check the results. This would be much helpful if you have a college project and you required photos for these. You don't really need to go back into the simulation, create a snipping or take a screenshot of it. This will generate a very good quality image for yourself, and you can just cut, copy and paste it wherever you require. And another important thing is the load factor. I'll just talk about it in a minute. Let's just go ahead and close this Word document. So since we're back to our model, let's go to results and press list buckling factor of safety. So the buckling factor of safety that we have obtained is 7.0121. So roughly it's 7. That means the load that is required to actually buckle this support bracket is actually 7 times what we have given. In most places, as a general rule of thumb, it is expected that the buckling factor of safety of whichever component that they are using must be more than 3. And another one that you need to consider is to increase the load factor or the buckling factor of safety for a model. All you need to do is just maybe you can add a stiffener. It can either be along the axis, horizontal axis, or can be along the vertical axis. And you will be working upon that as a challenge. That's it for this video, guys. Let's have a quick summary of all the content that we've looked in this video. So first we learned what is buckling. We then learned what Euler's critical load for buckling is. After this, we had a look at the relationship between the shape of buckling and the type of fixtures used, and also their effects on buckling. We then proceeded on to the software part and performed a simple buckling analysis on a cyclonic separator stand. Well, that's it for this video, guys. I hope you understood the concept, and I'll meet you again in the next one. Bye. Finite element analysis using SolidWorks. And in this video, we will be talking about fatigue analysis. In specific, we will be performing a fatigue analysis on a S hook, which we normally find on chains. All right, so before we continue on with the video, let's just have a small discussion of all the content that we will be covering in this video. So the first one would be, we'll be talking about what is a fatigue analysis, and then we'll be talking about the different applications of fatigue analysis. After that, we will be discussing about the SN curve in fatigue analysis, and I'll also explain you what an endurance limit is. Then we'll just move on to the software part. We'll do a normal stress analysis of the S hook, and then we'll continue on to do a fatigue analysis of S hook, and then I'll explain you the difference between the 4 different types of fatigue analysis modules that are available in SolidWorks. And at the end of this video, we will be giving you a brief explanation about the different results that you can obtain by running a fatigue analysis. So let's move on. So the first topic that we are discussing is, what is a fatigue analysis? You see, fatigue analysis establishes whether your model is susceptible to fatigue damage when it is subjected to a varying load. But before we actually understand what fatigue analysis is, we need to be aware of 2 very important things. One is fatigue failure, and the other one is fatigue damage. So what are fatigue damage and fatigue failure? When components are subjected to loads which vary with time, they tend to fail at stresses well beyond their ultimate yield strength. This is known as fatigue failure. So why does fatigue failure even occur? It is due to the formation of microscopic cracks in the surface of the material. As we continue our cyclic loads, the crack continues to increase in its size. Once it reaches a certain length, it leads to fracture. This is actually well visible in this model, which I've actually showed to you in this screen. So here you have a normal shaft, which has a load acting on both the directions. We have a small crack here, and at one point of time, it just experiences fracture. So how do we figure out whether a component will fail under fatigue? This is done by subjecting the model to a large number of constant amplitude cyclic loads and counting the number at which the fracture occurs. The test is then repeated to a large number of times with different applied stress values. We can plot the results into a graph, and this graph is called as the SN graph or the SN curve. The graph might actually seem a little bit overwhelming to many people in the beginning. It's not really that difficult. I'll just explain it to you. So here we have the SN curve for brittle aluminium with a certain grade, and you can see that in the y-axis we have the stress in megapascals, and in the x-axis we have the life cycles. So according to the graph, if the aluminium is subjected to 300 megapascals of stress, then the material will fail under fatigue stress with just 10 life cycles. The same way, if you subject it to around say 100 megapascals of stress, then the material will fail at around 10 to the power 6. That means around 1 million or 10 lakh life cycles. So using this curve, it allows us to calculate the number of cycles of load a material can experience before undergoing failure for a given range of stress. Fortunately, we don't need to perform the time-consuming tests yourself, as The data for these materials is published in many material handbooks and also many code books, and you can actually get the data online. The next point we will be discussing about is the endurance limit. You see, for some materials, especially ferrous metals, the SN curve becomes flat for lower stress values, and this is known as endurance limit. So what does this mean? Theoretically, the component or material can be cycled at this stress value for an infinite number of times, and it will never undergo fatigue failure. So for this material, let's say here we have the SN curve for steel, and here we have the SN curve for aluminium. We can notice that the SN curve of aluminium does not flat out, whereas the SN curve for steel starts to flat out at a stress value of around 30 ksi. So that means that 30 ksi of stress value, steel can theoretically endure almost infinite number of life cycles, and this is called as endurance limit. Now that we've actually had a brief discussion on fatigue failure, fatigue damage, and fatigue analysis, it is important that you also know a few applications of fatigue analysis. One of the most prominent ones is in spinal implants. When people have a few spinal impairments like scoliosis, what they do is they perform surgery on the spine and they place spinal implants. Spinal implants do is they provide support for our spine. So whenever the person is going to bend over, the spinal implant will also bend over. And one way to ensure that fatigue failure does not happen in these spinal implants is by running a fatigue analysis. Another important application, analysis of power transmitting shafts. The next common one is turbine blades. This is the area where majority of the fatigue will take place in turbine blades. We could go into the particulars about it, but we are really constrained by time. Another one is airplane wings. If anybody who has traveled in airplane or at least seen an airplane take off or land, you would have noticed that every single time an aircraft lands, the entire wing structure, this area just moves up and down. Because of that, the place where the wings connect with the fuselage, this area, will actually undergo a lot of stress and also cyclic repeated stress. Because of that, fatigue can occur. Another one is athletic shoes. You would have noticed, right? Every single time we buy a new shoe, for the first a week or two, our shoe would feel like brand new. It would have this certain amount of resistance when we are walking. But as we continue to use the wear and tear, what happens? The specific area in our shoe begins to wear out because you're moving your. This is because of anatomy of our feet. Every single time we try to lift our foot up, only this area lifts up and this place is going to stay firm on the ground. Because of this, a lot of stress is being developed in this specific area of our foot, of our shoes. So what these big companies, big shoe companies like Adidas, Nike, Reebok, what they do is they run a fatigue analysis, and this is especially done for custom made shoes. So let's now move on to the software part of this course. Let me quickly go into the SolidWorks interface. All right, so I have opened SolidWorks. I'll just quickly go over and give Control O. So I've opened the S hook. It's a step file, so the software will be reading the model. You will also be provided the model. If at all you want to do this for your own practice, it will be linked below. Okay, we have our S hook here. So what we will be doing is we will be fixing this area, this place, and this part of our hook, and we will be running a small stress analysis with a certain amount of force acting in this way, and then we will run a fatigue study to determine how many cycles this S hook can experience before it undergoes failure. If you're still wondering where do we find this hex, just if you have a chain or any gold ornaments, you will be able to find the S hook. It's normally used to hold the two ends of our chain, and it helps us to remove it and put it back. This is fairly straightforward. All right, let me just go ahead and grab my SolidWorks simulation license. Okay, so now that it has come, let's go ahead and press new study. So before we actually move on with the fatigue study, it is actually important that we perform a static study or even a dynamic linear study, linear or non-linear study on this SO. because this is why we define the different parameters of our analysis. So I'll rename it as static hook, and I'll click tick. We'll just continue to do the usual stuff. For material, let's go apply our material, apply edit material. Since this is a part of a gold chain, the material that we will be applying is pure gold. So for that, let's go to other metals and scroll down to pure gold and hit apply. And the color of our material has changed. Close. Now we will be fixing our model. So the parts that we will be fixing are this curve, this bend, this end, and this cylinder. Because we will be applying a force from here. If we fix this one, we won't really get any results from this. Let's press OK. And the external load will be, we will be applying force of, let's assume 200 newtons. Okay. Let's run this directly. Run this study. Don't really need to mesh it because this is a very small model. We can use the automatic mesh here. Okay, so the solver has seen excessive displacements. So it's going to change the type of solving. So it will be changing to large displacement model. So let's press yes. Okay, we have our results. As you can see, we have a 1 Mrs. stress. Most amount of the stress is induced in this area of our hook. And this is exactly what we needed. With this data, we can run a fatigue study. Alright, let's go to a new fatigue study. For that, right click, create new simulation study, and we will be renaming it as fatigue hook. And let's go and press fatigue. As you can see, once I press the fatigue simulation option, we again further get 4 more different fatigue models. So the first one is a constant amplitude fatigue analysis. The second one is variable amplitude. The third one is a harmonic fatigue study. And the last one is a random vibration fatigue study. So don't worry about all 4 of this. I'll just explain them with the help of an example. So let me just quickly go over and open my Jamboard. Alright. So I have my Jamboard. For the exam, let's just take a normal cantilever as an example. Okay. So let me just draw here. So this side it is fixed, and we have the cantilever beam over here. Okay. And we have a force of, let's say, n newtons acting in this direction. Load versus time graph. So the load will be here as y direction. This is n, and the time will be t seconds in this direction. So at 0 seconds, we don't have any load, and we'll just mark it as 1, 2, 3, 4, 5. So each one of these are actually 10 seconds. All right. So at 0 seconds, the amount of load that is acting on this cantilever beam is 0. Okay. And at 10 seconds, what happens is we decide to give a load of n newtons in this direction on this cantilever beam at this point. So what will the load be in this graph? It will be around here. And I'll just mark this as, just for the sake of reference, let's make this a small n. It will be small n, all right? And it will be acting downwards direction, so it will be a positive load. And again, at 20 seconds, the amount of load acting on the cantilever beam is removed. So at this instant, it will be 0. Let's mark it here. At 30 seconds, the amount of load that is acting on this cantilever beam will be n, but
Here's the small problem. We will be at here, the load will be acting in the opposite direction. To mark opposite direction, I'll just change the color here. It will be here, acting in this direction. Ensure that it's the same magnitude, so it's smaller. And that would be, since this is acting in a different direction, you will be considering that as a negative load. And that is at 30 seconds here. Again, the next another 10 seconds goes by and the amount of load that is acting, it becomes 0. Now let's just plot all these graphs together. And now what happens is the same graph, the same pattern, it's followed again. What happens is the graph will look somewhat like this. And this is what constant amplitude fatigue loads are. At certain set intervals of time, you have a certain fixed value of load which is acting at a certain direction. As the time progresses, the load remains constant, but the direction in which the load acts changes continuously with respect to time. So the next one is the variable amplitude history data. This we can explain by comparing it with constant amplitude. The only difference between a constant amplitude cycle and a variable amplitude is that here in constant amplitude, the amount of load and the time interval, everything is fixed. But in variable amplitude, just as the name suggests, every single parameter here varies with respect to time. So here you can see that at this specific time instant, n value of load is acting in the downwards direction. So we have a positive n value. And according to the graph, after a fixed interval of time, the direction in which n is acting will be reversed, but the magnitude will remain same. But that is not the case with variable amplitude fatigue tests. With time, the direction and also the value of the acting load will keep on changing. The next one is the harmonic fatigue study. The harmonic fatigue study is actually much similar to the constant amplitude study. In harmonic study, the loading and unloading will follow a sinusoidal graph. Let me just go to the workboard. So this is for a constant amplitude study. The graph for harmonic study will be somewhat similar to this. It will be a sine graph. That means it will follow the curvature of, most of you who have seen a sine graph or a cosine graph will be able to recognize this. This is how a harmonic study will be. So in a constant amplitude study, at 10 seconds for this example, we had n. Again, at 30 seconds, we had n, but in the different direction. So it was either an extreme value in a certain direction or an extreme value in the opposite direction. But in a harmonic study, we will be gradually increasing the load here. So let's say from 0 to the maximum value, we're not going directly from 0 to 100. We are approaching it and we are increasing the value of load gradually. And again, in the same way, we're not decreasing the value immediately to 0. We are reducing the value gradually and again changing the direction of the load gradually. So that's the main difference between harmonic study and the constant amplitude study. And the last one is random vibrations. Random vibrations, this module is mostly used to run fatigue study for components which experience a lot of vibrations. This is pretty self-explanatory. So we will be performing a constant amplitude study in this. I'll just go ahead and press OK. Okay, so here we are in the fatigue analysis window. Before we start, let's just go check the properties. Here you can see the mean stress correction. Here you can choose between Goodman model, Gerber model, or the Soderberg model. For now, for this analysis, we're not going to select any of these because these are not required for such a simple analysis. We'll just press none and press OK. Right click on the loading and let's add the events. Here you can see that the static analysis that we have performed has already showed up here as an automatically selected. You can see that there are four different types of loading. They are fully reversed, zero based, loading ratio, fine cycle peaks. So the first one is the fully reversed loading. In fully reversed loading, the load value is fully reversed for a set number of cycles. So let's say we are having 1,000 newtons of force of load which is acting in a certain direction, and it is oscillating between a positive and the negative directions. Essentially, what the software does here is that it changes the value of the load from positive side to negative for a single cycle, and the analysis is run for a set number of cycles. So in this case here we have set it as 1,000. So the load will be oscillating between a certain value. Let's say in this static analysis we have set our load as 200 newtons. So it will be 200 newtons for the first instant, and again it will become plus 200 minus 200, and it will continue on till we hit the required number of cycles. And the loading ratio for a fully reversed load is actually -1. The next one is the zero based loading. In zero based loading, the load is varied between 0 and the value of the load. So in the previous one, the fully reversed, what happens is that, so if our input load is around say 200 newtons as in our example, then the load will be oscillating between 200 minus 200 up until we reach the total number of cycles, so here 1,000. But in zero based, what happens is that it will initially be 200, again it will come back to 0, again it will go back to 200, again it will come back to 0. So this will continue on till it reaches 1,000. And this is also actually called as the on off load, since we're for one instant we are actually giving load, and for another instant we are removing the load, so which is effectively just offing the component. So next one is actually loading ratio. Loading ratio is nothing but a ratio between the maximum to the minimum load that the component will be experiencing. So here in our example we're giving say 200 newtons of load, and our loading ratio here, which is given by default, it is 0.5. That means that the load will be oscillating between 200 newtons to 100 newtons. So the maximum is 200, and 100 is actually 0.5 times of 200. So that means it is the minimum load will be 100. And in the same way, if your value is negative, then it means that the direction is also different from the initial value. So here 200 is our input value. Then if we have minus 0.5, then the minimum value will be minus 100 newtons. And the last one is find cycle peaks. Find cycle peaks is based on multiple reference studies. The program uses the stress results of the specified studies to find cycle peaks that give the highest alternating stress for each meshed node. An example of this would be if you are evaluating a scenario where a dead load is present. So in short, what this does is it will run multiple studies to identify the highest peak of the alternating stress among the studies that are mentioned by the user. And for now, we're not using any of these. We will be using the fully reversed one. And let's press OK. Our next task of action would be to add fatigue data to our model. So let's go and press the model and right click, apply or edit fatigue data. Once we press this, we have the material dialog box. Here you can see that the SN data is actually empty. So what we can do is we just go ahead and press the derive from material elastic curve. Initially it was fixed at define. That means the user will have to input the N and the S values manually. But we don't really want to do that. We will just press on derive from material elastic modulus, and the software will automatically generate one for us. We can either select based on austenitic steel curve or carbon steel curve. We'll select austenitic steel curves and press apply. If at all you wish to actually look at the SN curve, you have a small preview over here, or you can press on the view option here and it will open up a separate tab for it where you can pan over and select and check all the values. Let's just close this one, hit apply and close. Now we have everything set up. Let's go and run the simulation. You just press run this study, and all right, we have the results. And the results are actually in two separate options. The first one is the damage analysis result, and the second one is for the life. Let's discuss about the damage. So the input parameters for us were we gave a 200 newtons of force in this direction on this face, and you can notice that this area has been completely damaged. This is from the legend. From the legend, we can see that this color associates with 100% damage. That means this part has failed for the fatigue study that we ran, and also the amount, considering the amount of force that we gave. The next one is life. So in this option, we can actually check how many life cycles you can survive for. And this bend has absolutely failed, because here you can notice that the maximum number of life cycles this has survived is for 10 cycles. And after that, it has undergone fatigue damage or fatigue failure. So for 200 newtons, 1000 cycles, this has hook with cold material will not survive. And that's what we have concluded from this analysis. And if you have a link to practice this on your own, we will be giving the model down below. You'll get a hyperlink to access the model. You'll get the step file. Your task, if at all you're willing to practice, would be to run a similar simulation, but with a much lesser amount of load. I gave 200 newtons of load. You can give 50, 100, 75 newtons of load, whichever load which you desire. And you can run this study and see how many cycles your S-hook can survive. Well, that's it for this video, guys. Hope you've understood the concept. I'll meet you again in the next one. Bye.
Hey guys, welcome to our course Finite Element Analysis using SOLIDWORKS. In our previous video, we talked about how to perform a fatigue analysis on a component, and in this video, we will be performing a simple drop test of a PCB board. So now let's move on to the contents that we will be covering in this video. So the table of contents for this week are, first we will discuss on what exactly a drop test is, and then we will move on to the software part where I will just show you how to access the drop test panel in the SOLIDWORKS Simulation toolbar. Then we will be performing a simple drop test of the PCB board, and then we'll have a brief discussion of the results. Then we'll have a summary, and after that we'll be concluding the video. So the first topic is, what is a drop test? A drop test is a testing procedure that is used to check how rugged and resistant a component is to being dropped from a certain height. Most of us would have seen many YouTube videos where people actually compare 2 or 3 phones and drop them from a certain height and then evaluate how rugged a certain phone is based on how much damage the phone has suffered from the drop test. In the right here we have a simple drop test of a phone from a certain height, and this is performed in a SimScale software, and this is a drop test of a simple circuit board which was dropped from a height of around 2 meters. This was performed in SOLIDWORKS Simulation. So let's move on to the software part. Here I have our SOLIDWORKS main page open. We will be performing the drop test of a PCB board. I've actually provided the link for that model which we will be analyzing here. The panel down below, you can access it. I'll just hit Ctrl O. Since it is a step file, not a solid part file, it'll just take some time to read the model and generate it into a solid model for us. Press OK. Alright, we have our model here. Let me just go quickly set it up for us. Okay. Since this is an assembly of many different components, it opened by default in the assembly panel. I'll just go over to SOLIDWORKS add-ins and grab our simulation license. Okay, we have the simulation panel open. Let's just click it, and here let's press new study. This is the usual, it will just open the different simulation options that we have for ourselves. I'll just scroll down a little bit and go to specialized simulation. Here we'll see drop test. Just change the name to drop test PCB board and press the green tick icon. Okay, we have a model open in the simulation environment. So right off the bat, you can notice that the simulation options for performing a drop test is much different from what we do for a normal static analysis or a linear analysis. This is because the parameters that we use are much different from those kinds of analysis. There we need to fix a certain model, so we have a fixtures option, and then we need to apply a certain amount of load to it, for it loading module. So based upon the requirements, the options also change. Here we are not actually fixing the model nor giving any other external force. We're just taking the component up to a certain height and just then dropping it off on a certain surface. So first we'll just go and set material to our model. We'll give plastic, so press apply or edit material. We have the dialog box open. Scroll all the way down. Here we'll see custom materials. Under this we'll have the option called plastic. Here under this we'll have custom plastic. So that's the material that we will be applying. So give apply and close. You can notice that the color of the material has changed because I've given a default green color for that specific material in the properties. Here, and the rest of the components will just apply any metal to it. So again, press apply or edit material. We'll give alloy steel here. Hit apply and close. Okay, the color of these components is also changed. Our next course of action would be to mesh it. So let's go and hit create mesh. Here under mesh parameters, we need to do another thing. Give a curvature based mesh because we have lots of small holes and lots of curves and bends in the model. So a curvature based mesh would give you a much better and more accurate results. We'll make it as 9 here, and the rest will just set automatically. Hit the green tick. Let the solver just mesh it. Okay, our model has been meshed. Next, we need to define the different parameters of the simulation. So for that, we need to go to setup, define or edit. Here in this option, we are defining the drop height and the velocity at which the object will impact. So we're not going to define the velocity, we're just going to define the height at which the object is dropped. So under that, we have again two separate options. One is from centroid and the other one is from the lowest point. The main difference between these two is that the height whichever we give here, let's say for this here we have it as 1000 millimeters or 1 meter. So the distance it will take, the 1000 millimeter height, it will actually be taken from the centroid of this object and not anywhere else. And the lowest point, if we select this option, the 1000 millimeter will be from the lowest point which we define for dropping. And for our simulation, we'll just give it as from lowest point and 1000 millimeters. And then the next option would be to define the direction of gravity. Here you can notice that by default it is actually 9.81 meters per second square. This is actually the gravitational constant in Earth at sea level. If you want to change it, you can also change it. For example, if you want to test how well this object will get damaged when you drop it on the surface of Jupiter, you can just change the value to 24.8 meter per second square, and there you're dropping the object in Jupiter. So that's a bit of a good flexibility we have. Here we can change the value whichever we want. The next option is the target. This represents the ground or flow at which this object will be falling on. We have two options here. One is normal to gravity, and the second option is parallel to the reference plane. So what do these two mean? So when you select this option, normal to gravity, the object will fall, the orientation of the target will be normal to the orientation of the plane whichever we have selected for gravity. For example, here we have not selected any plane for gravity. Let's go ahead and do that. Let me quickly open the design tree. Here you can see that I've created a separate plane here. So we'll be selecting this plane as our gravity, this plane as our plane for gravity, and just collapse this one. And the next option will be going to normal to gravity. So what this does is our object, it will fall in this direction. This is actually denoted by the arrow mark here. Or you can choose a reference plane along which the object would fall. Here we're not actually doing that, we're just pressing on normal to gravity because I've already created a separate plane here along which I want my object to fall. So I'll just select normal to gravity. The next option here that we have is friction coefficient. By default we have it as 0. That means the object will be falling on a smooth surface. We could also make it rough by giving a certain friction coefficient to the surface. I'm not giving anything here because for now let's just keep it as 0. By default, the selection here is for a rigid target. If you don't want your target to be rigid, we can also make it flexible. Let's just go ahead and press that now. Here you can see that we have many more options here. The first one would be the normal stiffness of the object, or the tangential stiffness, the mass density, the target thickness. By inputting these values, we can accurately shape the target as per our requirements. You can also change the units in which you want it to be. It's either SI, English IPS, or metric system. So we'll just select rigid target and proceed on with that. The next option that we have is contact dampening. Contact dampening is normally considered for bodies that come into contact with each other during impact and have no interpenetration contact between them. Here the contact dampening is actually calculated as a viscous dampening force. For now in this simulation we're just giving contact dampening as 0, not changing its value. Now that we have set everything that's required, let's just go ahead and press the green tick. Okay. The next parameter we will be talking about is the result option. Here press the right click on the result options and press on define or edit. The result options in the property manager allows us to set the options for the output of the drop test analysis. The first one would be solution time after impact. The solution time after impact option is used to define the time period up to which the solver needs to perform the simulation after the drop impact. For example, here we are given the solution time after impact as 156.8 microseconds. That means that the solver will capture and solve whatever stress, forces or displaced in the model for about 156 microseconds after impact. Let's just reduce it to 100 because 156 will take a lot of time for us to simulate. And the next option we have are the save results. Under this again we have 4 different options. Here the first option is the save results starting from. So what this option does is that it instructs the program to start saving data from the moment at which the data is given. For example, here the default value is 0 microseconds. So what this does is it instructs the program to start saving the data from the moment of impact. We normally use this parameter after an initial study to specify the time window of interest based on the preliminary result. The next option is the number of plots. This option is used to set the number of plots that the program will save. After that we have the sensor list and also the number of graph steps per plot. We're not actually going to change any values around here. I'll just explain why that is in a few seconds. Let's just go ahead and press the green tick. Okay. The main reason here is because drop tests take a really long time to simulate. So when you actually define all these options, if you run the simulation with all these options activated, the entire duration of simulation will come around 8 hours. For 8 hours, the solver will run the program in the background, so the simulation will run for 8 hours. Because of that, we're not actually giving any options. I've already run the simulation beforehand, just before recording this video, so I'll just show that to you and explain the results. Then again, remember, you will be provided this model. If at all you want to try it yourself, you can download the model and do that yourself. So let's just go to the results which I've already performed. So these two are the ones. Let's click on drop test. Here we have 3 results. So the first one would be the stress, the displacement, and the amount of strain that is developed in the model. You can also go ahead and animate each one of those. Let's click on animate. Or you can also save it as an AVI file. Here select options. Here select on this drop down to decide on what type of compression algorithm you want to use. Let's press on full frames uncompressed and click on OK. Here you can decide how fast your simulation should run. You can either make it extremely fast by moving the bar to the extreme right, or you can make it extremely slow by moving it to the extreme left. We will set it at 125 and press on play. So it will just generate the frames. It will just create the frames and run the simulation for us. Here it is. You can see the type of deformation and where the strain actually occurs. You can also pause it at a certain instant. Look around and again play. You can do the same thing for all 3 options, the displacement and the strain. Well, that's it for the software part, guys. Let's move on to the summary. So in the beginning of the video, we had a brief discussion on what exactly a drop test means and where it is used. And then we performed a drop test of a PCB board in SOLIDWORKS Simulation. And then I explained you how to interpret the results. Well, that's it for this video. Hope you understood how to perform a drop test in SOLIDWORKS Simulation. I'll meet you again in the next one. Hey guys, so in this video we will be discussing on why should we perform a frequency analysis, and after that we will discuss what is a natural frequency and what is resonance, and once that is done, move on to discussing what is mode shape. After that we will talk about the different types of solvers that we have in SOLIDWORKS frequency analysis, and after that we will perform a simple frequency analysis of a support bracket using SOLIDWORKS Simulation. And in the end, we'll just have a summary. So let's get started with our video. The first question that we will be asking ourselves is, why should we perform a frequency analysis? A frequency analysis is used to determine the vibration characteristics of a structure or component that is being designed or is already designed. So why is it important for us to know how an object vibrates or at what frequency it vibrates? To understand this, we need to have knowledge of 2 topics. The first one is natural frequency and the second one is resonance. You see, all physical structures have natural frequencies. These are frequencies at which the structure will tend to vibrate when subjected to certain external forces. These frequencies are dependent on the way mass and stiffness are distributed within the structure. Whereas resonance is a phenomenon in which a dynamic force drives the structure to vibrate at its natural frequency. When a structure is in resonance, a small force can produce a large vibration response. So what does this mean in practice? When a force is applied to a physical object, it vibrates. When a force is applied at the object's natural frequency, it goes into resonance. And at resonance, the amplitude of vibration is at its highest. For a better understanding, let's take a guitar. When the different strings of the guitar are plucked, different sounds are produced. The type of sound also varies when the location at which the guitar is plucked varies. Similarly, all physical objects have multiple natural frequencies and can resonate under the right conditions. Sometimes the natural frequencies are excited by external forces acting on the object, which creates vibration. These vibrations may be so small that the human eye cannot see them. Sometimes these vibrations are desired and sometimes these vibrations are not. A good example for desired vibrations is the guitar, just as I explained. And the main reason behind us performing a vibrational analysis is to prevent or minimize the undesired vibration in a system. A good example where this is undesired and destructive is in the case of a wine glass. Wine glasses have a certain natural frequency in which they vibrate. So when we direct sound waves at those exact frequencies, resonance occurs, and this causes the wine glass to vibrate rapidly. And after some time, it just breaks. Another great example of resonance being destructive is the Mexico City earthquake, which occurred in 1985. During the earthquake, all buildings which had up to 6 to 15 floors were absolutely destroyed to rubble, whereas the rest of the buildings had a relatively minimal damage. After investigation, it was found that the frequency of the earthquake matched with the resonant frequency of the building, which had 6 to 15 floors. The next topic we will be talking about is the mode shape during vibration. A mode shape is the deformation that the component would show when vibrating at the natural frequency. The resonance frequency of the vibrating object will vary with different mode shapes. There are 3 different types of solvers which are used to perform frequency analysis. They are the direct sparse solver, the FFE+, and the Intel direct sparse solver. Based on our simulation, we can either select them manually or click on the automatic solver selection checkbox to automatically choose them. How they work and the specifics behind the working of each of these solvers is beyond the scope of this video. What I'll do is give you a brief explanation as to where these solvers are used. The automatic solver selection is the default option which is given to almost all types of simulation modules, be it static, buckling, thermal, or frequency. But should you decide to manually select each of these solvers, you can just click on this drop down box and select either one of them. In case of a multi-area contact problem, where the area of contact is found through several contact iterations, then the direct sparse solver is preferred. While all solvers are actually efficient for small problems, there can be a big difference in performance in solving large problems. In general, the FFE+ is actually faster in solving problems with degrees of freedom over 100,000. It becomes more efficient as the program gets larger. The direct sparse solver requires about 10 times more RAM than the FFE+ solver. It becomes faster with more memory available on your computer. This solver leverages multi-core processing capability and improves the solution speed for static and nonlinear studies. When the moduli of elasticity of the materials used in the model are very different, let's say in the same model you have 2 different materials like for example steel and nylon, then iterative methods could be less accurate than direct methods. In such scenarios, direct solvers are recommended. When performing analysis where there are no interpenetration contacts and bonded contacts, direct solvers tend to solve these much faster. So with this, let's move on to the software part. So let's start off by running a simple analysis of these 3 brackets. The main objective of our simulation is to determine which of these 3 brackets are most resistant to vibration. So here we have a normal bracket and then a thicker, it is a little bit more thicker in dimension, and then we have a normal bracket which has a stiffener. So what we will be doing is we will be performing frequency analysis on all 3 of these components individually and along with their assemblies, and we will be finding which of these 3 have the highest amount of resonant frequencies. So let's move to the software. So here is our stiffener. I've opened this up in SOLIDWORKS Simulation. To perform a frequency analysis, we just need to first go to New Study and press on the frequency option here. I'll just name it to Frequency Normal and press on OK. I've already given the material for this as cast alloy, the modeling tab itself, so no need to give any material right now. So our next course of action would be to give it fixtures. So right click on it and give fixed geometry. and we will be fixing these 4 holes. So I'll just do the same. Again, please always make sure that you select the cylinders, not the circle, because just a small mistake can give you varied results. So I'll just go ahead and press it, Ctrl 7, and press OK. So we fixed the geometry here. So the next one is external loading. Here the external loading is actually not the source of vibration. So this is one confusion most people have. Here the external load is just a static preloading which already exists in our component. So for example, let's say we already have a load of 100 Newton which is already existing on this bracket. So we want to find the resonance frequency of this bracket while we have the load on it. Only in that case we will be giving in the external load for this bracket. Right now we just want to find the resonance frequency of this bracket without any external loading. So we're not going to add any values to it. So our next task at hand would be to mesh it. So right click on the mesh and click on create mesh. Here let's go to mesh parameters and curvature based mesh. Here we'll set it as 4 millimeters. Now press on OK. And let's wait for the model to be meshed. Okay, our model has been meshed. Alright. Now let's run this study. So the simulation is done. Here we can see that we have 5 different options. So each one of these are different mode shapes, and we also have the respective resonance values for them. So the first one is the mode shape. Here you can notice that this part of the bracket will move up and down. We can actually animate this. So right click on it and press on animate. So let's just wait till it generates the frames. So you can see that this part of our bracket is moving up and down. Similarly, let's click on the second mode shape. So here you can see that this part is actually moving in opposite directions. So while this one is going down, this one is actually going up. Let's animate that. As I said, here's the animation. Let's press OK. So these are the different mode shapes of our bracket, and each of these mode shapes will have a different resonance frequency. We can actually check the resonance frequency by going into results, right click on the results, and here click on list resonant frequencies. Here you can see that we have the resonance value in radians per second, hertz and seconds. So the resonance frequency of the first mode for this bracket is around 1755 hertz. So we'll just note that down. So we'll just remember that one. And let's go ahead and press close. We can also define how many modes we want in our simulation. So to do that, we need to go to the title here and right click on this and select the properties option. So as you can see that by default we have the number of frequencies radio button checked here, and by default we have the number 5 here. So the default is to calculate the lowest 5 frequencies which will occur to the bracket. So should you want to change the number, you can just press on these arrow marks to either increase or decrease, or you can just go ahead and change your number. So let's say you want to find 10, you just type 10. So by default it is always 5. So the next option that we have is the calculate frequencies closest to. So let's go ahead and click on the checkbox. So what this option does is that it calculates a n number of frequencies which are closest to the specified value. So let's say we are entering our input value as 2000 Hz and the number which is input here is 5. So here we have given the value as 2000 Hz. So what it does is it will calculate 5 frequencies which are closest to 2000 Hz. So for example, let's give the value here as 6000 Hz and let's run the simulation again. As I've changed it, I'll just press run study. Okay, so we have our result here. So let's go to results, right click and list resonance frequencies. So here you can see that all of these values are somewhat closer to the 6000 we inputted here. Initially our first modal frequency was around 1700. Value which is given here was the resonant frequency of either the third or the fourth mode, and here you can see that it has changed entirely. So that's the function of that option. Now let's press on close and move on to the next option we have. And the next option is the incompatible bonding options. This option is used to define the type of bonding. So by default we'll have the automatic option selected here unless you manually change it. So what does this option do? By default the type of bonding which is given is surface to surface bonding. So during a simulation occurs, if the surface to surface bonding contact slows down our solution considerably, then what the solver does is it automatically switches to node to surface bonding. The next one is the simplified bonding option. This option is used to override the default surface based bonding and resume to node based bonding. We need to use this option only in case we run into performance issues when solving models with extensive contact surfaces. The next option is the more accurate option. So what this option does is that it applies the default surface-based bonding contact. This results in a longer solution time than the node-based contact formation, but it also gives us a much more accurate solution. So to summarize what all three of these do, the automatic option is used to automatically switch between either surface-based to node-based or node-based to surface-based based on our solver. The simplified option is used to exclusively select the node-based bonding, and the more accurate option is used to exclusively select the surface-based bonding. After that we have the solver options. Here, as we just discussed, this option is used. This is where we select the type of solver. I've already discussed on what direct sparse solver is, FFE plus and Intel direct sparse. So I'll not be talking much detail about that one. A frequency simulation of our normal bracket. We'll now do the same for the thick bracket. I'll just go ahead and minimize this one. And let me open the thick bracket. Right off the bat, you will be able to notice that the thickness of this bracket is much higher than the normal one. So we'll just do the usual. Let's go to simulation. I've already activated the license here. Go to new study. And under new study, you press frequency. I'll name it thick bracket. And I'll press OK. Control 7. Since I've already given the same material to this one, we'll just not define anything. Let's go to fixtures, fixed geometry. So what I'm doing right now is just the same that I did for the normal bracket also. So I'll just be fast forwarding it right now in the clip. Once I get the results, I'll just show it to you. Okay, so here we have our result here. So as discussed, let's go ahead and look at the resonant frequencies. Right off the bat, you can notice that the resonance frequency of this thick bracket has actually increased. So for the normal bracket, the resonance frequency of the first mode was around 1700. And for the thick bracket, the resonant frequency of the first mode is 2480. So the main reason why I am specifically mentioning the first mode is because by default, what the solver does is it gives you the lowest 5 frequency values. So that's why I'm considering mode 1 as our benchmark for comparison. So you can notice here that it is 2480. It is about 724 Hertz, much more than that one. So let's just note down this value, and now we'll go ahead and do the frequency analysis of the bracket which has a stiffener. So I'll just close this one and minimize this. I'll go to the bracket with stiffener. So it is this one. Let me just maximize this one. Here you can see that we are right now in the model option. Here you can see that I've added a small stiffener in the bottom just to increase the stiffness of the bracket. So I'll just press Ctrl 7. Let's go to new study. So right on, from here on, it's going to be the same again. So I'll just be fast forwarding the video. Okay, so we have our result here. Here you can see that the mode shape is somewhat similar in all three of the brackets. Even in the normal bracket, this horizontal metal piece was actually moving up and down, and in the thick bracket it was moving up and down. The same way here, even for this bracket with stiffener, it is actually moving up and down. So let's go and check the results here. Let's press on the list resonant frequencies option. So here you can see that the frequency value for the first mode shape is around 2486, and for the thick bracket the mode value which we received was 2480. So here you can notice that not only have we increased the resonance frequency of this bracket, but we have also saved a lot of weight. I'll prove that in the end, because I've also done a small mass comparison for all three brackets. So just remember, right now the bracket stiffener has the highest amount of resonance frequency. So it is 2486. Let's go ahead and close it. So now that we've actually done a frequency analysis for all three brackets, let's go ahead and do the same frequency analysis for the assembly also. So I'll just minimize this one and open the assembly. So the first assembly that I will be opening, that of the normal bracket. So I'll just minimize this. So this is our assembly. Here you can notice that we have two brackets over here and here, which are actually holding the entire assembly up. This is just a plain model which I made. So the main purpose of these two brackets is to hold this one. There will be more structure here. Just for the sake of simplicity, I've not added it here. So let's go ahead and run the simulation. Here, let's go to parts, and I've already given the material for these two as cast alloy steel. So for the base, this part, for this one also we'll mention it as cast alloy steel. So let's go to apply favorite material and select cast alloy steel. The next job of ours will be to fix the geometry. Again, this is all much similar to what I've already done. Let's press the select the holes. I'll just select all of them, because in these holes is where the entire geometry will be resting upon. So let's press OK. The next job would be to mesh it. So let's just create a mesh, curvature based. Let's go to mesh parameters, curvature based, and we'll make it a 15mm mesh. So what this means that the maximum size of our mesh element would be 15, and the rest of the parameters are just taken in automatically. We can also change these ones if you want to, and the minimum element size would be 3. Let's press OK and let the solver mesh it. So we have received our meshed model. The only thing that is left is for us to run the study I've already run this study myself in the background. This takes a little bit of time for me, so I'm just not showing it on screen. So let's just press on frequency 1 to look at our results. Just remember, I've used the same options here. I didn't change anything. The mesh was the same one. I used a 15mm mesh, and here also we've used the cast alloy steel, and the fixtures are also much more similar. Are the same actually, not similar. So let's press the first one. So here you can see that the first mode shape would be up and down. So the entire structure will be moving up and down. It is also much similar to the mode shape that we received for the individual bracket. That means this horizontal piece will be moving up and down. So let's check the resonant frequency of this one. Go to options, right click, go to list resonance frequencies. Here you can see that it is 234.79. That is the lowest resonance frequency for this one. We'll keep this one as the benchmark for the rest of the brackets too. I'll press close. I'll just minimize this one and move to the next. So this is with stiffener. So I'll just maximize this one. Again, I've already run the simulation for this one with the same parameters. I've not changed anything. So let's select the first amplitude. Again, it's the same. It's moving up and down. Here you can see similar mode shape, similar to the one which we saw in the individual frequency analysis. So I'll just press Ctrl 7. Let's go to results and list resonant frequencies. Here you can notice that it is 276.87. This is much higher than the resonant frequency without the stiffener. Again, let me note down this one and press close. I'll move to the thick one, and this is the thick model. Here again, these are the thick brackets. I've also run the simulation for this one. Ctrl 7, the first amplitude. Again, it's the same. It's moving up and down. There are the other amplitude also. The only reason why I'm not comparing those ones is because our benchmark right now, which is the first amplitude. So press on results and let's list the resonant frequencies. So here you can see that it is 298. It is actually much higher than the 276 of the bracket one. So let's just note this one now and press close. Ctrl 7. So now that we have all the required data, let's now compare all the resonant frequencies for all the brackets. So let me just jump into the PPT. Okay, so here is our PPT. We have our normal bracket, thick bracket, and also the bracket with stiffener. The values that we obtained are, for the assembly model, the normal bracket had a resonance frequency of 234 Hz. This is not the resonance frequency of just the bracket. This is the resonance frequency of the entire assembly. For the thick bracket, it was 298 Hz, and for the bracket which had a stiffener, it is 276 Hz. The same way, we also performed an individual analysis. So for this one, it is 1756 Hz for the normal bracket. For the thick bracket, the individual resonance frequency was 2480. And for the bracket with the stiffener, it was 2486 Hz. So I also checked the mass of each of these brackets. You can actually do that directly in the SolidWorks. Before ending this PPT, I'll just show it to you, don't worry. So the mass of the bracket for this one is 1461 grams, that is 1.4 kgs. For this one, it is 2.191 kgs. And for this one, it is 1534 grams. So here you can notice that the increment is much higher, and here it is very less. So with a much higher increment in mass, we have reasonable increment in the resonance frequency values. Here with very little increment in mass, we have a much appreciable increment in the resonance frequency. So this is the major application of frequency analysis. This is actually used to compare different resonance frequency of different structures to determine whether they are safe or whether they are not safe. So I'll just go to the SolidWorks window and show you how to calculate the mass of this bracket. Okay, so I've opened SolidWorks, and here is our bracket. This is the normal bracket, not the thick one, not the one with the stiffener. So how you find the mass is you just go to Tools, Evaluate, Mass Properties. Here in this dialog box, you'll have pretty much all the information that is required. Here you can see the mass value. It is 1461 grams. So how the software calculates is once we define a material to it, the software will have a database of the density of the material, and based on the geometry, it will calculate the volume. So mass is just volume into density, and we get our mass here. And we also have our volume, the surface area, center of mass, all the data here. And for now, the only thing that we require is the mass. So that's here. And let's just close it. Okay, so let me just jump back into our PPT. Let's move on to the summary part. So in the beginning of this video, we first talked about what natural frequency is and what resonance is. After that, we had a brief discussion on the different examples of resonance. And after that, we had a discussion about mode shapes of vibration. Once we were done with that, we performed a frequency analysis for a bracket. And then in the end, we compiled the results and had a brief discussion on the resonance frequencies of each of those brackets. For your challenge, we have something which is interesting. Let's go to the SolidWorks assembly. So here I have the bracket assembly. This is just a normal bracket without increased thickness or stiffener. So let's just go to the frequency analysis. Here in the beginning of this simulation, I've told you the main function of the external loads was to take the static preloading into consideration. So what does static preloading mean? So here you can see how the brackets function. They're just used to support this base on, say, a wall or a cantilever or whatever. So these are just brackets which are used to support something. Here I did not give any values of external load while running a simulation of the bracket. Let me just open the individual brackets. So here we have our bracket. So while we actually ran the frequency analysis, we gave our external loads as 0. But for your challenge, what it will be is we will provide you all model of the thick bracket, the model of the normal bracket, and the model of the stiffener bracket. You will have to find the mass of the loading object. We will either give it to you as a model or it will be mentioned in the question. And then with the help of that, you will be performing an external load. And then you will be creating a proper report of your findings with step-by-step data for everything. Well, that's it for this video, guys. This is the last video of our course. So this is where we part ways. Hope you've enjoyed our content and most importantly, learned something. If you do feel that you've learned something, do recommend our courses to your friend circle. Hey guys, welcome back to the course FEA Analysis using SolidWorks. I hope all of you are doing good. In this video, I will be running a simple buckling analysis on a bracket. Then I will be adding a stiffener to the bracket and show you how to increase the buckling factor of safety for a model. So this example will be especially helpful to attempt the buckling analysis challenge. So towards the end of the video, I'll just give you a brief introduction as to what you are expected to do in the buckling analysis challenge. So let's just get started. So this is the bracket. I've already opened that in SolidWorks. And what I will be doing is I will be applying a load of 2000 Newton or 2 kilonewton on top in this face. And the rest of the bottom faces, these 4 faces will be fixed. So I'll go into SolidWorks add-ins and grab our SolidWorks simulation license. Just click it to activate it. So we have our license here. Once we have the simulation license activated, let me quickly go and click it. Now I'll press new study. This will give us all the simulation that we can do on SolidWorks. I'll just rename this as frame buckling. Select buckling module and then the green tick. This is done. I'll just do the usual. Let's assign a material for it. I'll just give cast alloy steel. Once that is done, let's go define the fixtures for this one. The bottom portion. Let's go select these ones. Make sure that you don't mess up the selections, because there's a huge difference between selecting a face and then selecting an edge. Since we're selecting only the faces, we need to make sure that we've selected only the faces. Control 7, isometric view. External load will give force 2 kilonewton, that is 2000 newtons on this face and the green tick. And another important one is meshing. So what I'll be doing is I'll set a mesh control for this single piece alone, because this is where majority of the buckling is going to occur. So I'll set a 1.5 into 1.5 millimeter mesh for these selected faces. And then we'll give a normal mesh for the rest of them. Let's just create mesh, the green tick. So we have our meshed model. As I just said, here you can see that the mesh is much more finer than the mesh in these areas. Just press Control 7 and let's run the simulation. And we have the results here. You can see that the buckling factor of safety at this instant for this model, when 2000 newtons of force is applied on this face, it is 13.89. So how do we increase the buckling factor of safety without really changing the dimension or the material that we use? One method to do that is by adding stiffeners, and that's exactly what we will be doing right now. Our target here is to get a buckling factor of safety of around 20. So our stiffener, let's just make a stiffener first and see how much load factor it's going to give us, and then we can alter the stiffener, the location, the dimensions of the stiffener, and then obtain our required load factor. Okay, for the sake of saving time, I've already made the stiffeners here and I'm just showing it directly to you. So if you're thinking, oh, how is this so difficult? No, it's really not that difficult. So what I did here was I just went into the front plane and created this sketch, okay, and then extruded it from mid plane so that this body will join with this body. Okay, it's very simple, not much of an issue. So what we will be doing here, this one will have stiffeners and the other one which we already ran, we did not have any stiffeners. So let's go into SOLIDWORKS add-ins and let's press SOLIDWORKS Simulation and grab our license. Once we have our license, I'll just press Simulation, New Study, Buckling with Stiffener. That will be our name. Select Buckling and press the green tick. Once we are in the simulation interface, I'll just go and give my favorite material here as cast alloy steel. Since we already gave cast alloy steel, it is important that we also give cast alloy steel here also. And the fixtures, fixed geometry. Select all the bottom faces and green tick, Control 7. External loads. I'll ensure that I give the same amount of load as the previous example. So it is 2000 newtons. So it will be 2 kilonewtons. So 2000 newtons. And I'll just run a normal mesh. We can give mesh and run so that we don't again need to press the run the study option again. Okay, so if you can see that the simulation has run, and there is one difference that you must have noticed. The load factor for this model with stiffener has almost increased by a value of 1.5. So before it was around 14.2, now it is around 15.7. So that means by simply adding one small part here, we were able to increase the load factor by a margin of 1.5. So what we will be doing right now is we will be further trying to increase the load factor. We'll keep our target as 20. Okay, so how will I do that? I'll just go to evaluate and use the design study. Here let's set the variables, add parameter. So before I move on to variables, it is important that you know that the only parameter which we will be changing is the location of the stiffener, nothing else. Okay, so the two parameters which define the stiffener are this one. This is the vertical length, vertical position. The next one is the horizontal position. So it's somewhat hidden here. I'll just press it, 10, and I'll mark it as horizontal. And I'll just press OK. Here I'll increase the maximum to 25. The same here also. So it will give us much more play here. And the minimum is 5. And the step, let it be a 7. So the next one is the buckling factor of safety. Let's go and grab it from the simulation. Since our target here is 20, we will be setting the minimum constraint as 20. So let's go into constraints and select add sensor. Don't worry about those many buckling factors of safety. So what I did was I just imported this model from the previous main one. So all the constraints whichever we set there also came in here. So that's not going to be an issue here. So mass properties, we'll go to simulation data. Here select buckling factor of safety. Once we've selected that, press the green tick. And here we need to change the constraint as 20. Since our target here is 20, we're adding it as 20. And instead of less than, it will be greater than. Oh, it changed here also. Again, we'll change it to 20. And the goals, the same condition. Since the model is imported, all the values have come here. Instead of mass properties, simulation data. Buckling factor of safety and the green tick. Our goal is to maximize it. And now that we have everything that is required, so the total number of active scenarios here is 25. It will run the simulation and check all the values 25 times based on the constraints and the goal. The only variables here will be the position of the stiffener. So I'll just give run and we'll just wait for it. Alright, so you can see that the solver has finished the design study and we have obtained, this is the optimal value. You can also notice that there are many more values which are more than 21. So there is scenario 4, scenario 10, scenario 15 and scenario 5. But among these 4 acceptable scenarios, only scenario 5 is given to us as optimal condition. So the main reason behind this is because in our goals we set the buckling factor of safety as maximize. So that means that even if we get, let's say, thousands of values, the optimal value will be the one which is maximum. So this will be the end of this simulation. We've achieved our goal right now. So this is a good example to show you how a simple change in the design increase the factor of safety of your models. So for your challenge, you will be given the model of the cyclonic separator which I simulated in the previous video. Let me just quickly open that. So this is the cyclonic separator which you will be given. The challenge here is that you should increase the buckling factor of safety of your stand, much similar to the simulation which I did. But the condition here is that you should not change the material, you should not change the dimension of your stand, and you should stick to the force values that we have given. So how do you do it? Let me just quickly go to isometric view. So the first thing that you will be required to do is remove these 3 and make a separate model of it. So how you can do that is selecting these 3 models, the middle cyclonic separators, control right, and you can suppress this model. Once you suppress this, you can actually save this as a separate part file. go to File, Save As, and you can select it wherever you want. And one important thing is this part, and you can save it wherever you want. I've already made a simple part file, so I'm not going to be saving it again. So I'll just hit cancel, and let me go grab that part file. Here is our part file. So to obtain our buckling factor of safety, so what you will be doing is initially you will be applying a certain value of force here directed downwards. That will cause buckling on these 4 legs of the model, and you will be given a certain buckling factor of safety, and also you will be receiving a target. So similar to how 20 was our target, the target for this will be available for you in the question, and your goal would be to create a stiffener in such a way that you will be increasing the buckling factor of safety of this model. So how you will be doing is, let's just go to Sketch and select Sketch and draw the profile of the stiffener, whichever you have in your mind, in this sketch view, and then offset it and then extrude it. You will also be given the extrude thickness of your sketch. This is to ensure that no abnormally big stiffeners are made, which are just not practical. And that's it. So once you create your stiffener, apply loads from the top part, notice how much buckling factor of safety you're getting, and then go to evaluate and run a design study on this. So similar to how I did it in the previous example, just create your stiffener and run a design study based on the position of your stiffener. You will get different buckling factors of safety for different positions of the stiffener. Find the most optimal position and submit it. Well, that's it for this video. I hope you all have a proper understanding of what is expected from the challenge. Well, that's it for this video. I'll meet you again in the next one. Bye.